Planets are supposed to hold themselves together, but what happens when one gets too small? Scientists are now exploring the limits of planetary gravity, and the answer is stranger than you think. How tiny can a world be before it can't even keep an atmosphere or itself intact? What gravity stops working actually means. Gravity is everywhere, and yet it's one of the most invisible forces in the universe. You feel it every second of your life. You don't float out of bed, your coffee stays in your mug, and the Earth spins you along at nearly 1,700 kilometers per hour without you even noticing. But what happens when a world gets too small? Does gravity just stop? Do the laws of physics suddenly turn off for tiny planets and asteroids? The truth is simpler and stranger than you might think. Gravity never stops working. It doesn't flick off like a light switch. It doesn't disappear below a certain size. Every object with mass, no matter how tiny, pulls on every other object. The real question isn't whether gravity exists on a small world. It's whether gravity is strong enough to do anything meaningful. And here's where things start to get fascinating. There are thresholds, real measurable thresholds where gravity can no longer sculpt a world. Imagine a ball of rock drifting through space. If it's too small, its own gravity isn't strong enough to overcome the rock's rigidity. The material resists compression, resists rounding, and the object remains lumpy, jagged, irregular. In other words, it can't pull itself into a smooth sphere. Gravity is there, tugging, pulling, whispering, but the rock is stronger than the tug. This is the first threshold, self-rounding. A planet isn't just a chunk of rock. It's a world where gravity has conquered material strength. When a body passes this threshold, its interior pressure increases toward the center. The rock begins to flow slowly over millions of years, and a sphere emerges. Below this size, it stays as a potato, a diamond-shaped asteroid, or a jagged fragment from a cosmic collision. Gravity tries, but it fails to dominate. The second threshold is the ability to hold an atmosphere. Every gas molecule in a planet's air is in motion. Some zip along slowly, some rocket away like bullets. A small world with weak gravity cannot hold these molecules close. Hydrogen escapes first, then helium, eventually even nitrogen and oxygen, depending on temperature. Mercury and the Moon are the perfect examples. They have gravity, yes, but it's too weak. Their atmospheres are thin, patchy, temporary, constantly stripped away by the sun's radiation and solar wind. Gravity exists, but it's not enough to cage the air, to let a world breathe steadily, or to support clouds, wind, or weather. The third threshold is even more subtle, the retention of loose material. Gravity is what lets soil stick to a planet, lets dust, rocks, and boulders cling instead of drifting into space. On tiny asteroids, even a small shove can send a rock hurtling away forever. Regolith, the dust covering a planet or moon, can escape during meteor impacts or even thermal expansion from sunlight. Gravity is there, tugging, but it's almost irrelevant. A world too small cannot hold its own skin together. Its surface is fragile, transient, almost like a memory of a planet rather than a functioning world. So when scientists talk about gravity stops working, they're not lying. They're talking about these thresholds. It's not about the force disappearing. It's about gravity failing to perform the essential jobs that define a planet. Rounding a mass into a sphere, capturing an atmosphere, and keeping a world's surface intact. Below these limits, an object is still there, but it's no longer a planet in the classical sense. It's a cosmic lump, drifting, tumbling, barely held together, where gravity whispers but doesn't command. And once you understand these thresholds, you start to see the universe differently. The asteroid belt between Mars and Jupiter is no longer just rocks floating in space. It's a gallery of worlds where gravity is a weak painter struggling to shape, hold, and preserve. Each irregular shape, each barren fragment tells a story of failure, not of absence, but of insufficiency. Gravity is present, but it's not enough to be a master. The three gravity regimes. Gravity doesn't just work or fail. It has regimes, zones where it behaves differently depending on size, mass, and structure. Think of it as a spectrum, from planets that dominate everything in their path down to dust grains barely feeling each other's pull. The first regime is what we intuitively call planetary gravity. This is the kind of gravity you're used to, the gravity of worlds that demand respect. It shapes continents, controls oceans, and dominates atmospheres. Planetary gravity is strong enough to pull a mass into a sphere, to trap gas and dust, to mold molten interiors over millions of years. Earth is an example. So is Mars, Venus, or even Ceres in the dwarf planet category. In this regime, gravity is the boss. Nothing resists it for long. Rocks bend, atmospheres cling, and worlds become self-contained systems. This is the gravity that makes a planet a planet. It has purpose, authority, reach. Step down a notch, and you enter rubble pile gravity. This is the twilight zone of the cosmos. Asteroids like Bennu and Ryugu live here. They are gravitationally bound, yes, but barely. Their surfaces are loose collections of boulders and dust. Gravity holds them together, but it's a weak glue. Push too hard or spin too fast, and they fracture, tumble, or shed material into space. In this regime, gravity is present, but it's negotiating constantly with inertia, spin, and collisions. These worlds are chaotic, unpredictable, beautiful in their fragility. A rubble pile can be nearly spherical, almost a planet, yet one small impact or fast rotation can tear it apart. Gravity whispers here, and the cosmos listens only half-heartedly. And finally, there's molecular dominance, the regime of objects too tiny to ever feel like worlds. Here, gravity is dwarfed completely by other forces: electromagnetic interactions, chemical bonds, thermal motion. A grain of cosmic dust, a pebble floating in space, gravity exists, but it's irrelevant. Molecules dominate. Forces at the atomic and molecular level dictate structure, shape, and movement. No atmosphere sticks, no sphere forms. This is the bottom of the gravity ladder, the domain where mass exists. But gravity is impotent against the natural order of matter. Understanding these three regimes transforms the way we see the universe. It's no longer a simple picture of planets floating in space. There's a gradient, a hierarchy, a scale of influence. Gravity is a continuum. At the top, it rules. In the middle, it negotiates. At the bottom, it barely makes a whisper. And when we start plotting real objects on this spectrum, from Earth-sized planets to icy asteroids to tiny pebbles, we can begin to answer the central question: how small can a planet be before gravity stops working? It's not just about numbers. It's about forces, thresholds, and behavior. Every object in space has a story, and that story is written in the strength and weakness of gravity. Early assumptions: size was everything. For centuries, humans looked up at the sky and assumed that size meant importance. The first telescopes barely resolved the planets as more than points of light, yet their movement across the heavens made them extraordinary. Ancient astronomers, from the Babylonians to the Greeks, defined planets not by composition, not by physical characteristics, but by motion. The word planet itself comes from the Greek planetes, meaning wanderer. Anything that moved differently from the stars earned the title. The Sun, Moon, Mercury, Venus, Mars, Jupiter, and Saturn were all wanderers, dancing against the fixed backdrop of stars. They were considered divine, celestial, and, crucially, large. Size mattered because the visible brightness of a planet gave the illusion of mass, dominance, and power. The Moon and Sun, enormous in the sky, were treated as planetary entities of their own class. The concept of a planet as a world with measurable physical properties simply did not exist. Motion and visibility were the defining criteria. When Copernicus proposed a heliocentric system in the 16th century, the discussion remained abstract. The planets' sizes were still unknown, their surfaces invisible, their internal structures a complete mystery. Astronomers had no tools to measure gravity, no understanding of internal pressure or planetary cohesion. The assumption was that larger celestial bodies were inherently planetary and, by extension, important. Anything smaller, like asteroids or comets, were anomalies, oddities wandering through space with no defined place in the cosmic order. Galileo's telescope in 1609 began to challenge these assumptions. He observed Jupiter's moons, discovering that not all celestial bodies orbited the Earth. Venus displayed phases, proving that not all wanderers moved on perfect circular paths around our planet. These observations forced astronomers to question the relationship between motion, mass, and significance, but size remained a dominant heuristic. After all, the smallest moons and irregular asteroids were invisible to the instruments of the time. The human mind, limited by what it could see, equated size with planetary status. Even into the 18th and 19th centuries, when astronomers like William Herschel began cataloguing Uranus and later discovered moons and small bodies in the solar system, size was still a key criterion. Celestial objects that were small, irregular, or faint were rarely classified as planets, even if they orbited the Sun and shared other planetary traits. For example, Ceres, discovered in 1801, was initially hailed as a planet. Its diameter was roughly 950 kilometers, small compared to the classical giants, but it occupied an orbit in the asteroid belt, a region that was soon found to be full of similar bodies. Within a few decades, the notion that size alone could define a planet began to crumble, though the initial bias remained. Big meant planetary, small meant minor. This mindset created a blind spot in early astronomy. Scientists could map the heavens, chart motion, and calculate orbits, yet they had no concept of the physics that actually makes a planet a planet. There was no understanding of hydrostatic equilibrium, the principle that allows a celestial body to pull itself into a sphere when gravity overcomes the strength of its material. There was no concept of escape velocity, no awareness that a planet's ability to hold an atmosphere depended on gravity's strength relative to thermal motion of gas molecules. Instead, size and brightness were proxies for importance, and early astronomers measured worlds by what they could see, not by what they were. It wasn't ignorance, strictly speaking. It was a limitation of perspective. Without telescopes capable of resolving small bodies, without understanding of material physics or gravity in quantitative terms, the simplest way to classify objects was by appearance. Motion and size were immediate and observable. Internal structure was entirely invisible. This method produced remarkable accuracy for the time. It allowed humans to predict planetary positions, plan eclipses, and navigate the oceans, but it left a huge gap in understanding. Planets were defined by a mixture of perception, tradition, and visible characteristics, rather than by objective, measurable physical laws. As observations became more precise, however, anomalies began to appear. Small bodies like Vesta, Pallas, and Hygeia, discovered in the early 19th century, challenged the simple size-based paradigm. These objects shared some characteristics with planets. They orbited the Sun, had stable trajectories, and maintained cohesive shapes. Yet they were tiny, irregular, and vastly smaller than Ceres or the classical planets. Astronomers began to realize that there was no clear line between planet and asteroid, based solely on size. Motion alone could not justify planetary status. The first cracks in the old framework appeared, and the question emerged. Perhaps there was more to being a planet than size, brightness, and motion. At the same time, Newton's work on gravity provided the missing piece. He mathematically defined the force that holds worlds together, explaining why planets, moons, and stars are spherical at sufficient mass. Gravity was universal, but its strength relative to the material being pulled determined whether a world could form a round shape or remain a lumpy fragment. Suddenly, astronomers could move beyond the illusion of size as a measure of planetary importance. They could begin to calculate thresholds. At what point does gravity dominate material strength? At what mass and radius does a world become spherical? At what point does it hold onto an atmosphere or maintain internal differentiation? These were the questions that finally allowed science to move past the simplistic, centuries-old equation of big equals planet. The journey from motion-based definitions to physics-based understanding was gradual. Even as telescopes revealed more asteroids and dwarf planets, the old assumption lingered. It took the discovery of Kuiper belt objects and icy worlds beyond Neptune to force a reckoning. Suddenly, Ceres, Pluto, Eris, Haumea, and Makemake had to be evaluated not by how large they appeared, but by their ability to meet physical criteria: self-rounding, atmospheric retention, internal cohesion. Size was not enough. Shape mattered, composition mattered, gravity mattered. This transition marked the birth of modern planetary science, where the identity of a planet is not a function of perception, but a consequence of the laws of physics. By the late 20th century, astronomers had developed a robust framework. Any body above a certain mass and radius, capable of achieving hydrostatic equilibrium and with sufficient gravity to hold or shape its environment, qualifies as a planet. Anything below that threshold becomes a dwarf planet, asteroid, or minor body. Motion and visibility are irrelevant. What matters is whether gravity dominates, whether the material yields, whether the world asserts itself as a coherent, spherical entity. This insight changed planetary science and reshaped our understanding of the solar system's structure. Why size alone failed as a metric? Size seemed intuitive for centuries. A large world, visible across the night sky, should naturally be a planet. Small objects, irregular and faint, must be minor, right? But nature doesn't obey simplicity. The first problem is the spherical assumption. Early astronomers assumed that all planets, by necessity, were round. It seemed obvious. Planets in the sky were bright, smooth, and consistent, unlike stars that twinkled. But the assumption ignored material physics. Not every celestial body achieves a sphere. Gravity competes with the internal strength of materials. Ice, rock, and metal resist compression. Only above a certain mass does gravity overcome these forces, slowly reshaping an object over millions or billions of years. Below that threshold, small worlds stay irregular, potato-shaped, or jagged, no matter how long they orbit the Sun. This failure becomes clear when observing asteroids. Take Eros, for example. Roughly 34 kilometers long and 11 kilometers wide, it is an elongated, lumpy body. Gravity exists, but the asteroid is too small for self-rounding. Its shape is determined not by its orbit or motion, but by material strength. Similar cases include Bennu, Ryugu, and many Kuiper belt objects. All are small, all have irregular forms, and all defy the old size-based definition of a planet. If size were the only metric, these worlds might be misclassified or ignored entirely. Size also fails when considering composition and density. A small icy world can achieve a sphere more easily than a rocky one of the same size, because ice is weaker and more malleable under pressure. Conversely, a tiny rocky body may resist rounding completely. A rigid rock that is twice as massive as a small icy object might remain potato-shaped, while the icy body becomes spherical. Size alone cannot account for these material-dependent differences. Physics, not apparent diameter, determines whether a body qualifies as a planet. Atmospheric retention further undermines size as a metric. Mercury and the Moon are smaller than Earth and Mars, yet they cannot hold substantial atmospheres. Venus, similar in size to Earth, retains a thick atmosphere because its gravity is sufficient. A small icy planet in the outer solar system may retain a tenuous nitrogen atmosphere, while a similarly sized rocky body closer to the Sun cannot. Clearly, the ability to host an atmosphere is not strictly about diameter. It is about the balance between gravity and thermal motion, not sheer size. Another complicating factor is spin and rotation. Rapidly rotating small bodies like Haumea in the Kuiper belt become ellipsoidal rather than spherical. Its mass is sufficient to pull itself nearly round. But rotation stretches it along its axis, producing a shape that challenges the classical spherical assumption. Again, size alone cannot explain these variations. Gravity, composition, and spin together determine planetary form. Ultimately, the spherical assumption problem reveals a deep truth. Being a planet is not about being big, bright, or easily observed. It's about whether gravity dominates a body's material, whether it can achieve self-cohesion, whether it can shape itself and its environment. Size is a contributing factor, but it is neither sufficient nor reliable as a standalone criterion. Understanding planets requires understanding forces, pressures, and thresholds, not just measurements across the sky. This insight transformed planetary science from ancient astronomy to modern astrophysics. It prompted the reclassification of objects like Pluto, refined our definitions of dwarf planets, and reshaped the way we explore the solar system. Rather than counting points of light or relying on visibility, scientists now measure mass, radius, density, shape, and rotation. They calculate internal pressures, escape velocities, and material strengths. Size alone failed because the universe does not reward simplicity, it rewards physics. For centuries, people assumed that size was everything. Bigger meant important. Brighter meant a planet. A small irregular rock, not a planet. Just a minor body. It seems simple, intuitive, obvious. But nature doesn't care about what seems obvious. And the universe is full of surprises. The first problem is the spherical assumption. Early astronomers thought all planets had to be round. It made sense. The planets they could see, Jupiter, Saturn, Earth, appeared smooth, symmetrical, bright, and perfect in the night sky. They assumed all planets shared these features, but that's not how physics works. Shape is not determined by observation, it's determined by forces. And the main force sculpting a planet is gravity. Gravity pulls everything toward the center of mass. That's why big planets are spherical. They are massive enough for gravity to win over the strength of the material they're made of. But here's the catch. Small worlds don't always have enough gravity. Their materials resist compression, hold their shape, and refuse to yield. The result? Lumpy, elongated, or irregular objects that may orbit the sun just like planets, but look nothing like the smooth spheres we imagine. Take asteroids, for example. Eros, Bennu, Ryugu. These are small, rocky, or icy bodies drifting through space. Bennu is only about 500 meters across, yet it has hills, craters, boulders, and jagged edges. Gravity is there, technically, but it's so weak compared to the rigidity of rock that the asteroid has no chance of rounding itself. It's spinning slowly, wobbling in its orbit, barely holding itself together. If size were the only rule, we might misclassify Bennu as a planet. But physics says no. Gravity cannot dominate here. The body is a cosmic lump, not a world. Composition also changes the game. Icy bodies and rocky bodies of the same size behave differently. Ice is weaker than rock. It deforms more easily under pressure. That means a small icy object can achieve a roughly spherical shape at a size that would leave a rocky object jagged and irregular. Imagine a snowball and a rock of the same diameter. Tap the snowball and it shifts, smooths, and yields. Tap the rock and it holds its shape, unbending. In space, gravity acts like a slow tap over millions of years. The weaker the material, the easier it is for gravity to shape it. Size alone doesn't capture this subtlety. Even the ability to hold an atmosphere cannot be predicted by size alone. Gravity's job is to pull molecules close and keep them from escaping. But the escape of gas depends on thermal motion, the speed at which molecules move, which is determined by temperature. A small icy planet far from the sun might hold a thin nitrogen or methane atmosphere. A slightly larger rocky planet close to the sun may fail to hold even a tenuous layer of air. Mercury is smaller than Earth, but its gravity cannot retain a significant atmosphere. Venus, slightly smaller than Earth, can hold a thick, crushing atmosphere. The difference isn't just size. It's the balance between gravity and the energy of the molecules it's trying to keep. Rotation complicates things even more. Some small worlds spin incredibly fast. Haumea, a dwarf planet in the Kuiper belt, rotates so quickly that its shape is stretched into an ellipsoid, almost like a rugby ball. Gravity is strong enough to pull it into something close to a sphere, but rotation distorts the result. If we judged planetary status by diameter alone, Haumea would fail to make sense. Its rapid spin and irregular shape tell us that size cannot be the sole criterion. Gravity, mass distribution, composition, and rotation all interact in subtle ways. Even the ancient assumption that visible brightness correlates with size and importance is misleading. A small reflective icy body far from the Sun can appear bright enough to catch a telescope's eye, while a larger, darker, rocky object nearby might remain almost invisible. Size, visibility, and apparent brightness are unreliable indicators of whether gravity dominates. They don't tell us if a body is truly a planet in the physical sense. In essence, the universe does not reward simplicity. It doesn't let us assign categories based on what we can see or what seems intuitive. Objects in space exist along a spectrum. Some are massive, spherical, atmospherically rich worlds. Others are tiny, irregular, and dominated by material strength rather than gravity. Some are in between, rubble piles held together by a weak gravitational handshake. Size alone cannot distinguish these categories. By the 19th and 20th centuries, astronomers began to see the limits of a size-based approach. The asteroid belt was no longer a few odd rocks. It was a vast collection of small bodies with widely varying sizes and shapes. The discovery of the Kuiper belt and trans-Neptunian objects added icy worlds that challenged the old framework further. Pluto, Ceres, Haumea, Make. They forced astronomers to ask, what makes a planet a planet? Orbiting the Sun wasn't enough. Size alone wasn't enough. Gravity, shape, and internal physics mattered more than appearances. The lesson is clear. The universe is nuanced. A planet is not simply a big round rock orbiting a star. It is a body where gravity dominates, where material yields, where shape, atmosphere, and internal processes are governed by forces, not luck. Size is a clue, yes, but it is never the whole story. By looking past size, astronomers could finally develop a framework that reflects reality, one based on physics instead of perception. This understanding reshaped the way we classify objects. Ceres was redefined as a dwarf planet. Pluto was demoted. Thousands of asteroids and Kuiper belt objects were categorized by their physical properties, not by how they looked or how big they appeared in a telescope. Today we can calculate precisely which bodies are massive enough to become spherical, which can hold atmospheres, and which are dominated by rubble or molecular forces. Size alone failed because it ignored the most important factor: gravity's ability to shape, bind, and sustain a world. The discovery of shape as a gravity test. For most of human history, planets were points of light. Even after telescopes arrived, they were still distant, blurry disks. People could track their movement, predict their positions, and calculate their orbits with stunning accuracy. But their true nature remained hidden. Astronomers knew where planets were and how they moved, but they did not know what planets were. That began to change when scientists stopped asking how planets move and started asking a different question. Why do planets look the way they do? At first, shape seemed like a cosmetic detail. A planet was round because that's how planets were supposed to be. No one questioned it. But as telescopes improved and smaller objects were discovered, that assumption started to crack. Some bodies were clearly not round. Others were almost round but not quite. Some looked stretched, lumpy, or misshapen, even though they orbited the Sun just like planets. This forced scientists to confront an uncomfortable realization. Roundness was not guaranteed. Shape had to be explained. The breakthrough came when astronomers connected shape to gravity. Not gravity as an abstract force pulling objects together, but gravity as a slow, relentless sculptor. If a body is massive enough, gravity pulls material inward from every direction. Over long periods of time, millions or even billions of years, this inward pull overwhelms bumps, ridges, and irregularities. Rock begins to deform, ice begins to flow. The object relaxes into the most stable shape possible. A sphere. This state has a name: hydrostatic equilibrium. Hydrostatic equilibrium is not a moment or an event, it is a condition. It means that at every point inside a body, the inward pull of gravity is balanced by the outward resistance of the material. The body is not collapsing, but it is also not holding itself up through rigidity alone. Gravity has become the dominant force shaping the object. This idea completely changed planetary science. Shape was no longer an accident or an assumption. Shape became a test. If a body is round because gravity forced it to be round, then gravity must be strong enough to overcome the internal strength of the material. If a body is not round, then gravity is too weak, and material strength is still in control. This simple insight created a clean, physical way to separate planets from non-planets without relying on tradition, visibility, or size alone. But this raised a deeper question. Gravity does not act in isolation. It is always competing against something. That something is material strength. Rock resists being crushed, ice resists being bent, metal resists deformation even more strongly. These materials can hold shapes, edges, and angles up to a point. Gravity has to be strong enough to overpower those resistances. Until it does, a body can remain irregular forever, even if it orbits a star for the age of the universe. This is why gravity versus material strength matters more than size by itself. Two objects can be the same size and behave completely differently. One can become round, the other can stay jagged. The difference is not their diameter. The difference is how strong their gravity is compared to how strong their material is. Once scientists understood this, shape became a diagnostic tool. A round object was not just visually pleasing, it was evidence. It meant gravity had crossed a threshold. It meant internal pressure was high enough to allow slow flow. It meant the body was no longer just a pile of material. It was a world governed by gravity. This realization allowed scientists to re-examine every object in the solar system. Asteroids were no longer just small planets that failed by size. They were bodies that failed a gravity test. Dwarf planets were not almost planets in a vague sense. They were objects that had passed some gravity thresholds, but not others. Shape, once ignored, became central. If gravity could make a body round, then gravity was strong enough to shape its interior, influence its surface, and potentially allow other planetary processes to occur. Shape was the first visible sign that gravity had taken control. First calculations: rock versus ice, temperature, and the planetary threshold. Once shape was understood as a gravity test, scientists needed numbers. They needed to know exactly how much gravity was required to overcome material strength. That meant calculations, real physics, not assumptions. The first thing scientists realized was that not all materials behave the same. A rocky body and an icy body of the same size do not respond to gravity in the same way. Rock is strong, ice is weaker. Under pressure, ice deforms more easily, especially over long periods of time. This meant that icy bodies could become round at much smaller sizes than rocky ones. That single insight explained a major mystery. In the outer solar system, many relatively small icy worlds are nearly spherical. In the inner solar system, rocky bodies of similar size remain irregular. Gravity hadn't changed. The material had. Scientists began calculating the critical radius, the minimum size at which gravity can overcome material strength and force a body into hydrostatic equilibrium. For rocky bodies, that radius turned out to be much larger than for icy ones. A rocky object generally needs to be several hundred kilometers across before gravity can dominate. Below that size, rock simply refuses to yield. It can support mountains, cliffs, and sharp edges without collapsing under its own weight. Gravity pulls inward, but it loses the contest. Ice tells a different story. Ice behaves more like a very slow fluid under pressure. Given enough time, it flows. That means an icy body can become spherical at a much smaller size, sometimes hundreds of kilometers smaller than a rocky equivalent. This is why moons like Mimas or Enceladus appear round even though they are far smaller than many rocky asteroids that remain misshapen. temperature adds another layer. Hot materials deform more easily than cold ones. Early in the solar system's history, many bodies were warmer due to radioactive heating and frequent collisions. That made it easier for gravity to shape them. As objects cooled, material strength increased, locking their shapes in place. This explains why some bodies are round today, even though their gravity seems barely sufficient. They crossed the threshold when they were warmer. Once they became spherical, cooling preserved the shape. Gravity didn't need to keep working as hard. The damage was already done. Scientists incorporated temperature into their models and realized something important. Hydrostatic equilibrium is not just about size. It is about history. A body's past temperature, composition, and internal heat matter just as much as its present mass. With these factors combined, material type, temperature, and gravity, astronomers finally had a working test. If an object was massive enough to overcome material strength at some point in its history, it could become round. If not, it would remain irregular forever. This turned hydrostatic equilibrium into a planetary litmus test, not a philosophical one, a physical one, a test that could be applied consistently across the solar system and beyond. It explained why Ceres is spherical while Vesta is not. It explained why Pluto is round while many Kuiper belt objects remain jagged. It explained why size alone had failed for centuries. A planet, in this framework, is not defined by orbit or visibility or tradition. It is defined by dominance. Gravity must dominate material strength. When it does, shape changes. Internal pressure rises. The object crosses a line from being a collection of matter to being a gravitationally unified world. This test did not solve every classification problem, but it gave scientists something they had never had before: a clear physical boundary. Shape was no longer cosmetic. It was evidence. And once shape became evidence, planetary science stopped being about what we see and started being about what gravity can do. Why this became a planetary litmus test. Once scientists realized that shape could be used as a gravity test, the next step was unavoidable. They needed numbers, not guesses, not traditions. Real calculations that could answer a simple but powerful question. How strong does gravity need to be to force a body into a sphere? That question sounds straightforward, but it opens the door to a surprisingly complex problem. Gravity is easy to calculate. Material strength is not. Gravity pulls inward, trying to crush everything toward the center. Material strength pushes back. Rock resists being squeezed. Ice resists bending. Metal resists deformation even more. A planet's shape is decided by which side wins this slow-motion tug-of-war. Early planetary scientists began by simplifying the problem. They imagined a perfectly uniform ball of material, sitting in space, pulling inward on itself. As you move from the surface toward the center, pressure increases. Every layer of material above presses down on the layers below. If the pressure becomes high enough, the material starts to behave differently. It stops acting like a rigid solid and starts acting like something that can slowly flow. That transition point is everything. For rock, this point occurs at much higher pressures than for ice. Rock can support tall mountains, steep cliffs, and sharp edges without collapsing. Ice cannot. Under pressure, ice deforms easily, especially over long timescales. This difference alone explains why icy moons often look like miniature planets, while rocky asteroids of similar size remain misshapen. The first calculations focused on rocky bodies. Scientists asked, how big does a rocky object need to be before gravity overwhelms the strength of rock? They found that below a certain size, gravity simply loses. The internal pressure is too low. The rock stays rigid. No matter how long you wait, the object never relaxes into a sphere. It stays lumpy forever. As the size increases, pressure at the center increases. At a certain radius, roughly a few hundred kilometers, the pressure becomes high enough that rock deep inside begins to deform. Not melt, not liquefy, deform, very slowly. Over millions of years, The interior flows just enough for gravity to smooth out the overall shape. This is why roundness takes time. Hydrostatic equilibrium is not instantaneous. It is the result of relentless pressure acting over geological timescales. Icy bodies cross this threshold much earlier. Because ice is weaker, it begins to deform under much lower pressure. That means an icy object can become spherical at a much smaller size. This is why moons like Mimas, Enceladus, and even some distant Kuiper belt objects appear round despite being far smaller than rocky bodies like Vesta. But material type was only part of the story. Temperature turned out to be just as important. Materials behave differently when they are warm. Hot rock flows more easily than cold rock. Hot ice deforms faster than cold ice. Early in the solar system's history, most objects were warmer than they are today. They were heated by radioactive decay, constant impacts, and internal friction. This meant gravity had an easier job back then. Scientists realized something crucial. A body did not need to be strong enough to reach hydrostatic equilibrium today. It only needed to have been strong enough at some point in its past. Once a body becomes spherical, cooling locks the shape in place. Gravity does not need to keep fighting. The object remains round even if its interior becomes rigid again. This explains why some objects sit right on the edge. They appear spherical, but calculations show that their present-day gravity barely seems sufficient. They crossed the line when conditions were more favorable. Their shape is a fossil of their past. With this understanding, scientists began refining their models. They combined gravity equations with material strength data and temperature profiles. They ran simulations. They compared predictions with real observations. Patterns emerged. Rocky bodies generally need to be roughly 600 to 800 kilometers in diameter to reliably reach hydrostatic equilibrium. Below that, most remain irregular. Icy bodies can do it at sizes closer to 400 kilometers, sometimes even smaller depending on composition and heat history. These were not arbitrary numbers. They came directly from physics. And once these thresholds were established, something remarkable happened. Shape became more than an observation. It became a diagnostic tool. If an object was round, scientists could infer that its gravity had once been strong enough to dominate material strength. If it was not, gravity had failed that test. This turned hydrostatic equilibrium into a planetary litmus test. Not a cultural test, not a historical one, a physical one. It allowed astronomers to sort objects based on what gravity could actually do, rather than how big something looked in a telescope. It explained why Ceres is round while Vesta is not, even though their sizes are not dramatically different. It explained why Pluto qualifies as a gravitationally unified world, while countless smaller Kuiper belt objects do not. It also clarified why size alone had misled astronomers for centuries. Size does not tell you how gravity compares to material strength. Composition and temperature matter just as much. Two objects of the same diameter can behave completely differently under gravity. Once this framework was accepted, planetary science entered a new era. Objects were no longer classified by tradition or visibility. They were classified by behavior, by whether gravity had crossed a threshold, by whether the object had become a self-governing world rather than a passive chunk of matter. Hydrostatic equilibrium was not chosen arbitrarily. It earned its place because it reflects a real physical transition. Below the threshold, material dominates. Above it, gravity dominates. That transition marks the birth of a planetary body in the physical sense. This is why shape still matters today. Not because spheres look nice, but because roundness is evidence. It tells a story about pressure, time, heat, and gravity. It tells us that an object is no longer just surviving in space. It has been reshaped by the forces that define planets. And once gravity can reshape a body, it can begin to do other things too. It can influence internal structure. It can separate materials by density. It can create conditions where atmospheres become possible. Shape is only the first signal, but it is the clearest one. This is how a simple question about shape became one of the most important tools in planetary science. And this is why, today, gravity is no longer judged by size alone, but by what it can overcome. The dwarf planet revolution, the discovery of Ceres. At the very beginning of the 19th century, astronomers believed they understood the architecture of the solar system. There were planets, there were stars, and there were comets that occasionally cut dramatic paths through the sky. The planets were few, orderly, and well-behaved, each following a predictable orbit around the Sun. There was Mercury, Venus, Earth, Mars, Jupiter, Saturn, and newly discovered in 1781, Uranus. Between Mars and Jupiter, however, there was something strange, a large empty gap that didn't quite make sense. This gap wasn't just a curiosity, it was a problem. By the late 1700s, astronomers had noticed a rough mathematical pattern in the spacing of planetary orbits, later known as the Titius-Bode law. It wasn't a law of physics, but it worked disturbingly well. Mercury, Venus, Earth, Mars, Jupiter, and Saturn all fell neatly into place. Uranus did too. But between Mars and Jupiter, the pattern predicted a missing planet, a world that should exist, but apparently didn't. So astronomers went hunting. On the night of January 1st, 1801, an Italian astronomer named Giuseppe Piazzi was cataloguing stars from the Palermo Observatory when he noticed something unusual. One faint point of light didn't stay fixed. Night after night, it moved slightly against the background of stars. At first, Piazzi thought he had discovered a comet, but the motion didn't match. The object followed a nearly circular orbit, far calmer and more planet-like than any comet known at the time. What Piazzi had found was Ceres. Ceres was immediately celebrated as a triumph. The missing planet had been found. It orbited the Sun between Mars and Jupiter, exactly where the mathematical pattern predicted. For a brief moment, the solar system felt complete again. Ceres was officially classified as a planet, making it the 8th planet known at the time. Astronomers across Europe rushed to calculate its orbit, refine its position, and understand what kind of world it was. But almost immediately, cracks began to appear in the story. Ceres was faint, extremely faint. Even by the standards of early telescopes, it was barely visible. As calculations improved, astronomers realized something unsettling. Ceres was much smaller than expected, far smaller than Mars, smaller even than many of the moons already known around Jupiter and Saturn. At first, this was brushed aside. Size had fooled astronomers before. Distance can make large objects appear small, and telescopes of the era were limited. But as years passed and measurements improved, the truth became unavoidable. Ceres was not just a little smaller than a typical planet, it was dramatically smaller. Then came the second shock. In the years following Ceres's discovery, astronomers found more objects in the same region of space. Pallas in 1802, Juno in 1804, Vesta in 1807. Each one orbited the Sun between Mars and Jupiter. Each one followed a stable, planet-like orbit. Each one was small. Suddenly, the idea of a single missing planet collapsed. The gap between Mars and Jupiter was not home to one world, but to many. A whole population of small bodies. The solar system was messier than anyone had expected. This forced astronomers into an uncomfortable position. If Ceres was a planet, then what were these other objects? Were they planets too? If so, the number of planets would explode. If not, why did Ceres qualify while the others didn't? The old definitions had no good answers. At this point, size quietly took over as the deciding factor. Ceres was the largest of the group, so it retained its planetary status. The others were gradually reclassified as asteroids, a new category created almost out of necessity. But this solution was more practical than scientific. It didn't explain why size mattered, it simply assumed that it did. For decades, this compromise held. Ceres remained a planet in textbooks well into the mid-1800s, even as its neighbors were demoted. But as telescopes improved further, and as astronomers began estimating mass and density rather than just brightness, the problem resurfaced. Ceres was not just smaller than planets. it behaved differently. Its gravity was weaker. Its influence on nearby space was limited. It did not dominate its orbital zone in the way classical planets did. Eventually, Ceres lost its planetary title. By the late 19th century, it was firmly placed among the asteroids, remembered as the first and largest of them. For a long time, the story seemed settled. Ceres was a historical footnote, a mistaken planet, a relic of an earlier era of astronomy. But the universe wasn't finished with Ceres yet. As physics entered astronomy in the 20th century, scientists began looking at celestial bodies in a new way, not just as points of light following paths, but as physical objects governed by forces, pressure, and internal structure. Mass mattered, density mattered, shape mattered. And when scientists looked again at Ceres through this new lens, something surprising emerged. Ceres wasn't shaped like a typical asteroid. It wasn't elongated or jagged like Vesta or Eros. It was round, not perfectly smooth, but clearly spherical. That meant something profound. Its gravity had been strong enough at some point in its history to overcome the strength of its material and pull itself into hydrostatic equilibrium. This was not a trivial detail. It was a physical threshold. Most asteroids fail this test. Their gravity is too weak. Their material strength wins. Ceres was different. Despite being small, it had crossed a line. It wasn't just a pile of rubble or a rigid rock. It was a gravitationally unified world. This realization forced scientists to revisit the old assumptions that had quietly guided classification for centuries. Ceres was too small to be a classical planet, but too round to be a typical asteroid. It sat in an uncomfortable middle ground. As space missions finally visited Ceres directly in the 21st century, the picture became even clearer. Beneath its surface lay evidence of internal differentiation. Its shape was stable. Its gravity, though weak, was functional. Ceres was not a failed planet. It was something else entirely. The discovery of Ceres had unintentionally exposed a flaw in planetary thinking. Size alone could not define a planet. Orbit alone could not define a planet. Visibility alone certainly could not. There was a deeper criterion waiting to be recognized, one rooted in gravity's ability to shape a world rather than simply move it through space. Ceres was the first object to force that realization, even if it took 2 centuries for the lesson to fully sink in. What began as a triumph of prediction became the opening crack in the classical idea of planets. And through that crack, an entirely new category of worlds would eventually emerge. Worlds that were neither planets nor asteroids, but something in between, governed by gravity just strongly enough to matter. This was the quiet beginning of the dwarf planet revolution. Kuiper Belt discoveries. Expanding the solar system. For centuries, astronomers assumed the solar system ended with Neptune. Beyond the 8th planet, the universe seemed empty, or at least devoid of large bodies orbiting the Sun in any orderly fashion. Comets would appear, streak across the sky and vanish, but they were considered transient visitors, not permanent residents. The idea that a vast population of worlds might lie in the cold, dark reaches beyond Neptune was mostly speculative. Yet hints had been around for decades. Theoretical work dating back to the 1950s suggested there could be a reservoir of icy bodies orbiting far from the Sun, a hidden zone that supplied the periodic comets that occasionally crossed Earth's path. Astronomers called it the Kuiper Belt, after the Dutch-American astronomer Gerard Kuiper, though he himself had never proposed an actual belt in the modern sense. For decades, the Kuiper Belt remained purely theoretical. Telescopes lacked the power to resolve tiny, distant, icy objects that reflected only a fraction of sunlight. Even in the 1980s, when CCD cameras became more common and detectors far more sensitive, astronomers had only glimpses of what might lie out there. Comets were indirect evidence. Short-period comets with orbits suggesting a distant origin hinted at a massive, unseen population beyond Neptune. Still, nothing had been confirmed. The breakthrough came in the early 1990s. Using improved telescopes and detection techniques, astronomers began systematically scanning the outer solar system. They weren't just lucky, this was deliberate, painstaking observation. Night after night, cameras captured faint points of light moving slowly against the fixed background of stars. Most were too small, too faint, or too distant to be resolved. But among them, the first confirmed Kuiper Belt object, KBO, was spotted in 1992. It was small, icy, and orbiting far beyond Neptune, in the region theorists had predicted decades earlier. Scientists named it 1992 QB1, a designation that would seem mundane, but actually marked a revolution. QB1 was not just a new asteroid. It was the first tangible evidence that the solar system extended far beyond the classical planets, that it was populated with countless small, icy worlds orbiting in a vast cold disk. The implications were enormous. The discovery validated theoretical predictions, yes, but it also opened a Pandora's box. If 1992 QB1 existed, then surely there were many more. Indeed, subsequent surveys quickly found dozens, then hundreds of objects, some as large as several hundred kilometers across, each with a nearly circular orbit in the distant reaches of space. These discoveries forced astronomers to confront uncomfortable questions about classification. Were these Kuiper Belt objects planets? They orbited the Sun like planets. They were massive compared to ordinary asteroids, far more numerous, and some even approached the size of known planets' moons. Yet many were not spherical. Most were too small for gravity to dominate their material strength. They were lumpy, irregular, jagged. Some were tightly clustered in orbital bands. Others were scattered, their paths elongated and eccentric. QB1 and its companions also highlighted a new reality. The outer solar system was far more diverse than anyone had imagined. These objects were composed primarily of ice, with rock mixed in, their surfaces coated in frozen methane, nitrogen, and carbon monoxide. They were remnants of the primordial disk, unchanged for billions of years, frozen in time at temperatures near absolute zero. Unlike the asteroids in the inner solar system, which had been repeatedly bombarded, heated, and fractured, Kuiper Belt objects were pristine. Each was a small, self-contained laboratory of the early solar system, offering clues to planetary formation that no classical planet could provide. The Kuiper Belt's existence also provided insight into the history of the classical planets themselves. Models of planetary migration suggested that Neptune and Uranus had not formed in their current positions. They had likely moved outward over time, scattering smaller bodies into the distant reaches, sculpting the Kuiper Belt into the vast disk we observe today. Some objects were trapped in resonances with Neptune, orbiting in perfect harmony that preserved their stability over billions of years. Others had been flung into eccentric orbits, forming the scattered disk, a chaotic fringe of icy remnants. By the mid-1990s, astronomers realized that the Kuiper Belt was not just a curiosity, it was a major component of the solar system. The number of KBOs discovered implied that the region contained hundreds of thousands of objects larger than 100 kilometers across. The total mass, though only a fraction of Earth's, was enough to shape the dynamics of the outer solar system and supply comets that entered the inner system on predictable timescales. The Kuiper Belt was a dynamic, structured, and surprisingly populated zone, challenging old notions of a solar system with neatly defined edges. One of the most profound consequences of the Kuiper Belt discoveries was the realization that size, orbit, and visibility were insufficient to define a planet. Many KBOs were larger than Ceres and approached the size of Pluto, yet they were icy, distant, and sometimes irregularly shaped. Classical definitions failed. Ceres had once been the largest object in the inner asteroid belt. Now, in the outer solar system, it was tiny, barely noticeable against the vast array of icy worlds. The discovery of the Kuiper Belt expanded the playground of celestial bodies, revealing that the solar system was a continuum, from the smallest rubble piles to the massive spherical giants we had long called planets. The observational techniques required to identify these objects were revolutionary as well. Astronomers had to account for extreme faintness, long orbital periods, and slow apparent motion across the sky. Unlike the classical planets, which were bright and visible to the naked eye, Kuiper belt objects required long exposure imaging, sophisticated software to detect motion against background stars, and repeated observations to confirm orbits. Each new discovery was painstaking, but the payoff was enormous. A glimpse into a population of worlds that had existed since the solar system's birth, largely untouched by the violent collisions and heating that had transformed the inner planets. By the late 1990s, the Kuiper belt had become a central focus of planetary science. It forced astronomers to rethink not only the architecture of the solar system, but also what it meant to be a planet. The region contained objects with a wide range of characteristics. Some were small and irregular, dominated by their own material strength. Others were massive enough to achieve near-spherical shapes, hinting that gravity was strong enough to assert control. These distinctions laid the groundwork for the next major challenge: the discovery of large Kuiper belt objects rivaling Pluto itself. Objects that would ultimately shake the foundations of planetary classification. QB1 had been the first faint point of light, a distant sentinel in the cold darkness beyond Neptune. But by the end of the 1990s, the Kuiper belt had grown from a theoretical curiosity to a bustling region populated with hundreds of worlds, some of which were massive enough to challenge Pluto's claim to planetary status. Each discovery revealed more about the processes that govern the outer solar system, the formation of icy worlds, and the limits of gravity's influence at extreme distances. These distant objects, once invisible, were no longer minor footnotes. They were active players in a revolution that would redefine how we classify planets, dwarf planets, and the boundary between the two. The Kuiper belt was more than a belt of rocks and ice. It was a laboratory for planetary science, a reminder that the universe does not arrange itself neatly. Every new KBO discovered carried the potential to redefine the solar system, to force astronomers to ask deeper questions about gravity, material strength, and what it means for a world to be a planet at all. In many ways, the Kuiper belt discoveries of the 1990s set the stage for one of the most dramatic shifts in astronomy since the discovery of Ceres over 190 years earlier. A revolution that would challenge our definitions, our assumptions, and the very notion of what a planet is. Pluto, Ceres, Haumea, and Makemake, worlds that redefined the solar system. By the late 1990s and early 2000s, the Kuiper belt was no longer a mere theoretical curiosity. It had become a cosmic frontier, a frozen wilderness at the edge of the solar system populated with countless small, icy worlds. Among the hundreds of objects discovered, a few stood out, massive enough to rival or even exceed Pluto in size, each with its own unique orbit, rotation, and composition. These were not mere asteroids or minor Kuiper belt objects. They were worlds in their own right, and their discovery would ignite one of the most dramatic debates in modern astronomy. What truly defines a planet? Pluto, discovered in 1930 by Clyde Tombaugh, had long been considered the ninth planet. It was small, icy, and distant, yet it had been elevated to planetary status almost immediately after its discovery. For decades, textbooks listed Pluto as the final member of the solar system's planetary family. Its size seemed unimportant at first, overshadowed by the novelty of being a new world orbiting far beyond Neptune. But Pluto had always been an outlier. Its orbit was highly eccentric, tilted relative to the ecliptic plane, and sometimes brought it closer to the Sun than Neptune. Its small size, only about 2/3 the diameter of Earth's moon, and icy composition made it unique among the classical planets. For years, these peculiarities were largely tolerated because Pluto was alone, the only known object of its kind. The late 20th century changed everything. With the discovery of the Kuiper belt and the realization that hundreds of icy bodies existed beyond Neptune, Pluto was no longer alone. It had peers, some of which were comparable in size or even larger. The first shock came in 2005 when astronomers using telescopes in Hawaii discovered Eris, a distant Kuiper belt object with an estimated diameter slightly larger than Pluto. Eris was massive enough that it forced astronomers to reconsider everything about Pluto's status. If Pluto counted as a planet simply because it was big and round, then Eris should count too. And if Eris was a planet, what about other similar worlds lurking unseen in the Kuiper belt? Eris was icy and bright, its surface coated with frozen methane, and it orbited the Sun at an average distance almost 3 times that of Pluto, in a highly eccentric path that carried it far into the scattered disk. Its mass was substantial enough to dominate its immediate region, yet its orbit was so distant that it interacted very little with the classical planets. The discovery of Eris highlighted a fundamental problem. The classical definition of a planet was inadequate. It relied on historical convention rather than a clear physical basis. Pluto had been classified as a planet for convenience and tradition. Eris, similar or even larger, could not be ignored. The solar system now contained multiple small icy worlds that challenged the old 9-planet framework. Shortly after Eris, other large Kuiper belt objects were discovered that further complicated the picture. Haumea, identified in 2004, was an elongated, fast-spinning object with a distinctly unusual shape. Unlike most spherical bodies in hydrostatic equilibrium, Haumea's rotation was so rapid that it stretched into an ellipsoid, resembling a rugby ball rather than a perfect sphere. Its surface was covered with crystalline water ice, and it had at least 2 small moons orbiting it, evidence that even these distant icy worlds could be complex systems with their own satellites. Haumea's odd shape posed an immediate challenge. Should a world that is round in some dimensions but distorted in others count as a planet? Its existence blurred the boundary between gravitationally dominated bodies and irregular minor planets. Makemake, discovered in 2005 shortly after Haumea, was another large, icy body orbiting the Kuiper belt. Slightly smaller than Pluto, it shared many of the same characteristics: a spherical shape, a frozen surface rich in methane and other ices, and an orbit far beyond Neptune. Unlike Haumea, Makemake rotated more slowly, allowing gravity to maintain a near-perfect spherical shape. The combined discovery of Eris, Haumea, Makemake, and dozens of other mid-sized Kuiper belt objects revealed a previously unseen continuum of worlds beyond Neptune, ranging from irregular rubble piles to nearly spherical icy planets. The accumulation of these discoveries forced astronomers to confront a stark reality. The solar system was not a neat hierarchy of 9 planets followed by a few small asteroids. It was a complex spectrum of bodies, many of which were comparable in size, composition, and orbital characteristics to Pluto. This challenged centuries of planetary tradition and demanded a new framework for classification. What distinguished a planet from a dwarf planet? Was orbital dominance important? Shape? Composition? Gravity? The old answers were no longer sufficient. One of the critical insights gained from studying these new Kuiper belt worlds was the importance of hydrostatic equilibrium in planetary classification. Eris, Makemake, and even Haumea, to some extent, were large enough that their self-gravity overcame the structural strength of their material, allowing them to achieve near-spherical shapes despite their distance from the Sun and their icy composition. Smaller objects in the same region remained irregular. Shape became a measurable, objective criterion. If gravity could dominate and pull a body into hydrostatic equilibrium, the object qualified for the upper tier of classification, regardless of orbit or historical convention. The discovery of these objects also underscored the role of location and temperature in shaping planetary characteristics. The Kuiper belt is extremely cold, with temperatures often below 50 Kelvin. Ices dominate these worlds, while rock forms only a smaller fraction of their interior. At these temperatures, material strength behaves differently than in the inner solar system. allowing even relatively small objects to achieve spherical shapes over long timescales. This meant that distant icy worlds could achieve hydrostatic equilibrium at smaller sizes than similarly sized rocky bodies closer to the Sun, emphasizing that composition and environment, not just mass or orbit, determined a world's physical character. The combination of these factors, size, shape, composition, and orbit, culminated in a historic debate within the International Astronomical Union. By 2006, the sheer number of large Kuiper belt objects and the physical realities revealed by telescopic and observational data forced a redefinition of what it meant to be a planet. Pluto, long considered the ninth planet, could no longer stand alone. Eris and Makemake were too similar to ignore. Hydrostatic equilibrium had emerged as a crucial criterion. A planet had to be a world where gravity dominates, pulling the body into a nearly round shape. Orbital dominance was introduced as a second criterion. A planet must clear its neighborhood of comparable bodies. Under these standards, Pluto and its newfound peers failed to meet the second criterion, while still qualifying as gravitationally rounded worlds. The compromise was to create the category of dwarf planets, objects that are spherical and gravitationally self-dominant, but do not dominate their orbital zones. The discovery of Pluto, Eris, Haumea, and Makemake thus reshaped planetary science entirely. For the first time, astronomers had a clear, physically motivated framework for categorizing distant worlds. These discoveries illuminated the continuum between the inner planets, the asteroid belt, and the outer solar system, demonstrating that the classical nine-planet model was an artifact of historical circumstance rather than a reflection of physical reality. They revealed that the solar system is layered, complex, and far more populous than had ever been imagined, with a spectrum of worlds ranging from tiny rubble piles to massive, nearly spherical dwarf planets. Perhaps most importantly, these objects forced scientists to confront the underlying principle that governs all planetary classification: gravity. Pluto, Eris, Haumea, and Makemake were not defined by size alone, by orbit alone, or by brightness alone. They were defined by whether gravity could dominate their structure, whether hydrostatic equilibrium could be achieved, and whether they could maintain that shape over astronomical timescales. This understanding would ultimately set the stage for the final part of the story, confronting the minimum functional threshold of gravity, the point at which a body transitions from a chaotic, irregular mass into a self-contained, gravitationally unified world. These discoveries also transformed how astronomers approached the outer solar system. Telescopes, both ground-based and space-based, were turned toward the Kuiper belt in systematic surveys. Each new world discovered contributed to a more detailed map of the outer solar system, revealing clusters, resonances with Neptune, and a complex interplay of dynamics that shaped the region over billions of years. Each new dwarf planet added weight to the argument that the solar system is not simply a set of planets followed by scattered debris, but a continuum governed by physics, where gravity determines identity as much as history or tradition. By the mid-2000s, the classification of Pluto, Eris, Haumea, and Makemake into the dwarf planet category was widely accepted, though not without controversy. The public was reluctant to demote Pluto, but the scientific consensus was clear. These worlds were all gravitationally rounded, icy, and complex, yet none dominated its orbital neighborhood. They represented a new tier of planetary bodies, bridging the gap between the inner planets and the myriad small objects populating the Kuiper belt. The discoveries of these worlds were more than just cataloging exercises. They changed our understanding of planetary formation, of how gravity interacts with material strength, and of the diversity of bodies that can exist in the same solar system. They provided a template for understanding exoplanetary systems, where similar populations of small, icy, and distant worlds may orbit stars far beyond our Sun. Pluto, Eris, Haumea, and Makemake revealed a solar system far richer and more complex than classical astronomy had ever imagined, and in doing so, they highlighted a fundamental truth. size and orbit are insufficient criteria. Gravity, and its ability to shape a world into hydrostatic equilibrium, is what defines the boundary between minor bodies and planets, and by extension, what separates chaos from order in the outer reaches of the solar system. Gravity's minimum functional threshold, what the outer solar system taught us. By the early 21st century, the solar system had revealed itself as far stranger and more complex than anyone of the 19th or 20th centuries could have imagined. From the discovery of Ceres in 1801 to the systematic exploration of the Kuiper belt in the 1990s, and finally to the identification of Pluto's icy peers, Eris, Haumea, Makemake, astronomers had been forced to confront a profound truth. The classical model of planets, neatly numbered and ranked by orbit or size, was inadequate. The new frontier was not only about cataloguing more worlds, it was about understanding what fundamentally makes a world a planet, a dwarf planet, or merely a minor object. At the heart of this question was gravity itself, not as an abstract force, but as the defining sculptor of planetary identity. Gravity is relentless. It never switches off, never takes a break, never forgets. Even the smallest object exerts it, pulling inward on every particle in its mass. But there is a critical point, a threshold, where gravity stops being merely a force among others and begins to dominate, reshaping a body from a chaotic assembly of rubble into a coherent, spherical world. This is the minimum functional threshold of gravity, the point at which self-gravity overcomes the strength of the material itself and achieves hydrostatic equilibrium. Below this threshold, material strength rules, and the object remains irregular, jagged and fragmented. Above it, gravity reigns, producing worlds with rounded shapes, layered interiors, and the capacity to maintain atmospheres or influence nearby bodies. The journey to understanding this threshold began subtly with the observations of Ceres. When Piazzi discovered it in 1801, no one realized that Ceres was the first window into this concept. Early astronomers focused on size and orbit, assuming a planet was defined by its motion or its position in the solar system. But centuries of observation revealed that size alone was misleading. Ceres, though small, was spherical. It was a physical proof that gravity could dominate material at a relatively modest scale. By contrast, other asteroids like Vesta or Eros remained irregular even when similar in size, demonstrating that composition and material strength mattered as much as raw diameter. Fast forward to the Kuiper belt discoveries, and the principle became clearer. Pluto, Eris, Haumea, and Makemake were all icy bodies orbiting far from the Sun, in regions where the temperatures approached absolute zero and sunlight was weak. Their surfaces were frozen solid, but their interiors had once been warm enough for gravity to exert its influence over geological timescales. Ice, weaker than rock, allowed these distant worlds to become nearly spherical at sizes much smaller than would be required for rocky bodies. Haumea, with its rapid rotation, even demonstrated that rotational forces could distort the shape, while gravity continued to dominate the interior, producing a unique ellipsoidal equilibrium. These examples allowed astronomers to quantify the threshold more precisely. For rocky bodies, self-gravity typically dominates when diameters exceed roughly 600 to 800 kilometers, depending on internal temperature and composition. For icy bodies, the threshold is lower, around 400 to 500 kilometers. Below these sizes, material strength prevents full relaxation into a spherical shape. Objects in this zone might be roundish, but minor irregularities persist. Above it, gravity gradually smooths out the surface, pulls the interior into layered structures, and creates a stable, coherent world. Understanding the minimum functional threshold had profound implications. It explained why Pluto, once thought alone in the distant solar system, could not claim unique planetary status. Eris, slightly larger and similarly spherical, proved that the threshold could be crossed multiple times among distant Kuiper belt objects. The threshold provided a physical basis to separate dwarf planets from the myriad smaller, irregular bodies populating the outer solar system. It was not a subjective judgment based on history, visibility, or cultural attachment. It was a measurable, scientific property. Hydrostatic equilibrium, central to this threshold, is the key to understanding planetary identity. When a body achieves it, gravity dominates everywhere, not just at the surface. The interior experiences enough pressure that the object can differentiate. Heavier materials sink toward the center, lighter ices rise, and layers form. Even without an atmosphere, the body becomes a self-regulating system, where gravity defines the shape, stability, and long-term evolution. Below the threshold, no such differentiation occurs. The body remains dominated by the rigidity of its constituent material. Mountains, ridges, and jagged edges persist. Collisions leave scars that gravity cannot erase. These smaller, irregular worlds are what we traditionally think of as asteroids, comets, or minor Kuiper belt objects. Temperature and time are inseparable from this threshold. A body may have insufficient gravity today to achieve equilibrium, but if it was warmer in the past, internal deformation might have been possible. Conversely, a body may cross the threshold in the present, but freeze before its interior fully relaxes, leaving subtle irregularities. This temporal dimension explains why some distant icy worlds are nearly spherical, while some similarly sized rocky bodies remain irregular. Gravity acts over millions to billions of years, sculpting the object slowly, inexorably. The concept of the minimum functional threshold also redefined how we interpret orbits and populations. Objects that failed the threshold remained passive members of the solar system, governed largely by external forces, gravitational perturbations from larger planets, collisions, and chaotic scattering. Objects above the threshold became active participants in their local environment, capable of retaining satellites, interacting dynamically with neighboring bodies, and, in some cases, sustaining transient atmospheres or surface changes. Even in the distant Kuiper belt, gravity mattered. It determined who could remain a coherent world and who would remain a loose collection of ice and rock. One of the most dramatic consequences of these discoveries is that they provide a universal standard for classifying worlds extending beyond our solar system. Exoplanets, discovered in the thousands over the past 2 decades, can now be evaluated not just by orbit or mass, but by the same fundamental principle. Does gravity dominate, and does it shape the body into hydrostatic equilibrium? Worlds that fail this test, no matter how many moons they orbit or how brightly they reflect their star's light, cannot be considered full planetary bodies in the strict physical sense. Gravity, in this way, is the arbiter of planetary identity across the galaxy. The minimum functional threshold also explains why the inner solar system appears different from the outer regions. Close to the Sun, rocky bodies dominate, and higher temperatures and stronger material strengths mean that only larger worlds, Mercury, Venus, Earth, Mars, achieve hydrostatic equilibrium. Smaller rocky asteroids remain irregular. Farther out, in the icy Kuiper belt, weaker ice allows smaller bodies to reach equilibrium, creating a new population of dwarf planets that would have been impossible closer to the Sun. Gravity is constant, but its relative strength compared to material resistance changes with composition and temperature. By the mid-2000s, the International Astronomical Union formally recognized this principle in their planetary definition. A planet must orbit the Sun, be massive enough to achieve hydrostatic equilibrium, and clear its orbital zone. Dwarf planets, on the other hand, also orbit the Sun and are massive enough to achieve hydrostatic equilibrium, but do not clear their neighborhood of other material. Ceres, Pluto, Eris, Haumea, and Makemake fit neatly into this new framework. Each had crossed the minimum functional threshold of gravity, becoming gravitationally rounded worlds, yet only the classical planets dominated their respective orbital zones. This framework resolved a centuries-long tension. It honored observations of shape, size, and composition, rather than relying on historical tradition. It explained why Pluto could no longer be counted among the classical planets without discarding the realities of the Kuiper belt. It clarified why Ceres, the first discovered dwarf planet, had always been anomalous. It crossed the gravitational threshold, but it did not dominate the asteroid belt. It provided a clear, objective criterion rooted in physics, connecting the discoveries of the 19th, 20th, and 21st centuries into a coherent understanding of what a world is. Perhaps most importantly, the concept of the minimum functional threshold underscores the role of gravity as the defining architect of planetary identity. Gravity is not merely a force that moves objects through space. It is a force that shapes them, organizes them, and dictates their internal structure. Every spherical world beyond the threshold is a testament to this quiet but relentless power, a laboratory of physics written into stone and ice across the solar system. Every irregular object below the threshold is a reminder that when gravity loses the contest to material strength, chaos persists, and a world remains a collection of debris rather than a coherent, self-contained entity. In the end, the discovery of Ceres, the Kuiper belt, and Pluto's icy peers, Eris, Haumea, Makemake, did more than expand our catalogue of solar system bodies. These discoveries forced scientists to confront the fundamental principles governing all celestial objects. They revealed the minimum conditions under which gravity could assert dominance, demonstrated the interplay of composition, temperature, and time, and established hydrostatic equilibrium as the universal yardstick for planetary classification. They transformed the way we understand worlds both near and far, replacing centuries of tradition with a precise, measurable, and physically meaningful standard. Through these distant frozen objects, we finally understand that planets are not defined by history, myth, or arbitrary size. They are defined by physics, by the quiet but inexorable authority of gravity, which, when strong enough, unites scattered material into coherent spherical worlds. And this understanding, born from Ceres and perfected through the discoveries of the Kuiper belt, will guide our exploration of the solar system and beyond for centuries to come, shaping not only our definitions, but our imagination of what it means to be a planet in the vastness of space. The physics of small gravity. Gravity is often thought of as an unshakable universal constant, something that tethers us to Earth and keeps the Moon in orbit. But gravity is also subtle, patient, and scale-dependent. On Earth, we take it for granted. Step outside, and it's always pulling. Jump, and it brings you back down. But what happens when you shrink the world beneath your feet? What happens when the planet itself is so small that its pull feels almost non-existent? To answer that, we have to leave intuition behind and look at the mathematics that define gravity at tiny scales. At its most basic, gravity is defined by Newton's law of universal gravitation. Every particle of mass attracts every other particle with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. In other words, the force pulling two objects together depends both on how much stuff they contain and how far apart they are. The equation is simple to write, but profound in implication. F equals sign Gx m1x m2 r2. Here, F is the gravitational force, G is the gravitational constant, m1 and m2 are the masses of the two objects, and r is the distance between their centers of mass. On Earth, we rarely need to think about the small r differences between the surface and a few kilometers above. It all feels uniform. But as the mass of a planet shrinks, as its radius shrinks, the interplay between mass and distance begins to change everything. Imagine a tiny planet, barely 500 kilometers across. That's about the size of Ceres, the first dwarf planet ever discovered. Its mass is only a tiny fraction of Earth's, roughly 1/300th. But radius matters too. Because gravitational force depends on distance from the center of mass squared, halving the radius doesn't just halve gravity, it multiplies its effect in the equation in a more complex way. The gravitational pull at the surface is proportional to the planet's mass divided by the square of its radius. G equals sign Gx m r2. Notice the R2 in the denominator. Gravity doesn't scale linearly with size. Double the radius without changing mass, and the pull at the surface actually drops. Reduce the mass without changing the radius, and gravity drops again. Combine the two, as in a tiny icy Kuiper belt object, and the pull at the surface becomes startlingly weak. Walking on such a world would feel almost like floating. Objects would weigh only a fraction of what they do on Earth. A stone dropped from shoulder height might drift slowly to the ground rather than thudding. A person could leap astonishing heights, though each step would be perilous, because the surface itself offers so little resistance. This relationship between mass, radius, and gravity helps explain why size alone is insufficient to predict the behavior of a world. A body might be visually large, but if it's composed of low-density material like ice, its surface gravity could be weaker than a much smaller rocky object. Conversely, a compact, dense asteroid could have stronger gravity than a larger, fluffier body. This interplay is crucial when we start talking about the minimum functional threshold of gravity, the point at which a body can even hold itself together, form a sphere, or retain loose material on its surface. To illustrate this, consider two hypothetical worlds. Planet A is twice the radius of Planet B, but made of ice, with half the density of rock. Planet B is smaller, but made of dense silicate rock. At first glance, Planet A seems dominant. It's larger, more imposing, perhaps even planet-like to the naked eye. But calculate the surface gravity, and Planet B might pull more strongly at the surface than the larger icy world. This is the subtle trap that early astronomers fell into when they equated size with gravity. Visual scale can deceive. Only by calculating the relationship between mass and radius can we truly understand the gravitational experience on a world's surface. Gravity also affects the internal structure of small bodies. On Earth, gravity is strong enough to compress the interior, create layers, and even drive tectonics. On tiny worlds, the pressure at the core is minimal. The internal material is governed as much by its own strength as by the planet's pull. A small asteroid might be a loose pile of rubble held together tenuously by its meager gravity, whereas a slightly larger dwarf planet has enough pull to overcome material strength, forcing it into a spherical shape over millions of years. In short, gravity dictates not just how objects move around a planet, but how the planet itself is structured. This leads to an important realization. Gravity doesn't turn off on small worlds. It just becomes weaker relative to other forces. On Earth, gravity dominates everything we experience. On a moon like Phobos, gravity is barely enough to hold a thin layer of dust. On a small Kuiper belt object, centrifugal forces from rotation or even minor impacts can eject material into space because the pull at the surface is so minimal. A planet's ability to retain an atmosphere, retain water, or even remain spherical depends on reaching a delicate balance. Mass must be sufficient to generate a gravitational pull that exceeds the material's internal cohesion. Too little mass, too small a radius, and the world cannot fully harness gravity's sculpting power. Another way to think about this is in terms of escape velocity, the speed needed for an object to break free from a planet's gravitational pull. On Earth, this is roughly 11 kilometers per second. On Ceres, it is about 0.5 kilometers per second. That's a factor of 20 lower. A strong gust could, theoretically, lift lightweight particles off the surface of a dwarf planet, while even a modest spacecraft can escape with minimal energy. Escape velocity is the visual, tangible representation of weak gravity. It tells us whether a planet can hold an atmosphere, whether it can retain loose surface material, and whether it can dominate its orbital zone. Even within small worlds, gravity is uneven. Imagine standing on a tiny, irregular asteroid. One foot may be only slightly closer to the center of mass than the other, yet the pull differs measurably. Small-scale irregularities matter. This is why rubble pile asteroids remain irregular. Their internal cohesion is minimal, and gravity cannot smooth them into spheres. But once a world reaches the minimum functional threshold, gravity starts to dominate over both material strength and local surface irregularities. smoothing mountains and valleys over geological timescales, and establishing a coherent shape. This explains why doubling the size of a planet doesn't simply double its gravity. Because gravity scales with mass and radius in a squared relationship, small changes in radius can dramatically alter surface gravity. Double the radius without increasing mass proportionally, and the surface pull diminishes. Double the mass, but increase the radius too much, and gravity still fails to reach a functional level. Gravity is not linear. It is a balancing act between the total mass of the world and the distance from its center to its surface. Temperature and composition also play into this balancing act. Icy worlds, common in the outer solar system, are more susceptible to gravitational rounding at smaller sizes than rocky worlds. Ice is weaker than rock, allowing gravity to overcome structural strength more easily. But ice is also brittle at extremely low temperatures, which can preserve irregularities. So even when a small body crosses the mass-radius threshold, its surface may retain scars, fractures, and ridges that reflect both internal and external forces. Finally, it's important to realize that gravity is not static over geological timescales. As a body accumulates mass from impacts or melts internally, its density can increase, changing the surface pull. Conversely, loss of material through collisions or outgassing reduces mass and weakens surface gravity. Tiny worlds are fragile not just in structure, but in gravitational stability. A marginally spherical dwarf planet today might have been an irregular rubble pile in the past. Or a loose collection of ice and rock could consolidate into a sphere over millions of years, as gravity slowly asserts itself. Understanding gravity at tiny scales is crucial for everything that follows in planetary science. It informs why some bodies become planets, some dwarf planets, and some irregular asteroids. It explains the hierarchy of the solar system, from Earth down to tiny moons, from Pluto to icy Kuiper belt objects, and from Ceres to even smaller asteroids. Surface gravity defines the physical reality of these worlds, their internal structure, their ability to retain atmospheres, and even their potential to host life. It is the invisible architect, shaping worlds in ways we can measure and predict, rather than merely observe. Without mastering the physics of small gravity, the mysteries of the dwarf planets, the Kuiper belt, and even exoplanets remain inaccessible. We can see them, detect them, and measure their orbits, but until we understand how gravity scales with mass, radius, and composition, we cannot fully grasp why some bodies form spheres, why some retain atmospheres, or why some cannot hold even loose surface material. Tiny gravity is not a weakness. It is a window into the fundamental forces that sculpt worlds across the universe, revealing the subtle threshold where chaos gives way to order, where a collection of ice and rock becomes a unified planetary object under the patient hand of gravity. Why doubling size doesn't double gravity. If you've ever imagined that a bigger planet must automatically feel like a heavier planet, it's time to rethink everything you thought you knew. Gravity doesn't work like a simple more size, more pull rule. In fact, doubling a planet's size rarely doubles the surface gravity, and sometimes it barely changes at all. The reason lies in the subtle interplay between mass, radius, and density, the triad that governs how strongly a world can grip its surface, hold an atmosphere, or sculpt itself into a sphere. Imagine two worlds. Both are perfectly spherical with the same composition. One has a radius twice as large as the other. At first glance, you might assume that the larger planet exerts twice the pull at its surface. After all, it contains more material, so its mass is higher. But gravity is deceptive. The force you feel at the surface depends not just on total mass, but on how far you are from the center of that mass. The larger planet pushes you farther from its center, and because gravitational force decreases with the square of the distance, this effect partially cancels out the increase in mass. Mathematically, surface gravity is calculated as G equals sign Gxm r2. Here, m is the mass and r is the radius. If you double the radius without doubling the mass, surface gravity decreases. If you double the mass, but the radius grows even slightly more than expected, gravity may barely increase. This is why tiny worlds like icy Kuiper belt objects can feel so weak, even when they are surprisingly large for their type, while dense, compact worlds exert disproportionately strong gravity. Let's make it visual. Picture Earth and a hypothetical twin twice its size. The twin is made of the same rock, so doubling the radius increases the volume by a factor of 8, because volume scales with the cube of the radius. Mass grows proportionally with volume if density stays constant, so the mass is 8 times larger. Surface gravity, however, is mass divided by radius squared. 8 times the mass divided by 4 times the radius squared equals 2 times the gravity. So yes, in this idealized case, doubling the radius results in only doubling surface gravity, not 8-fold. But now imagine a planet made of ice. Its density is lower, reducing mass, and the same doubling in size barely increases gravity at all. The takeaway is simple but profound. Gravity does not scale linearly. Small changes in radius or composition can dramatically alter surface pull. This principle explains why worlds like Pluto, Ceres, Haumea, and even smaller moons like Mimas and Enceladus feel weak gravity, while relatively tiny but dense asteroids can exert a noticeable pull at their surfaces. It also explains why early astronomers misjudged the significance of size. The largest object isn't always the strongest in gravity. It's the combination of size, mass, and density that matters. This nuanced understanding naturally leads to escape velocity, one of the most intuitive ways to visualize a planet's gravitational strength. Escape velocity is the minimum speed an object must reach to break free from a world's gravitational pull, assuming no additional propulsion. On Earth, this is about 11 kilometers per second. That's fast. Rockets achieve it with enormous fuel and engineering. On smaller worlds, however, escape velocity drops dramatically. Consider Ceres, roughly 500 kilometers in diameter. Its escape velocity is about 0.5 kilometers per second, roughly 2% of Earth's. A strong gust of wind could, in theory, loft light particles off the surface. On a tiny Kuiper belt object, escape velocity may be even lower, meaning that impacts from micrometeoroids or even internal outgassing can eject material into space, unopposed by gravity. Escape velocity is therefore not just an abstract number. It is a measure of a world's ability to hold itself together, to maintain an atmosphere, to retain loose surface material. Visualizing escape velocity can make the concept intuitive. Imagine standing on a small, icy moon. You toss a pebble straight up. On Earth, it arcs and lands nearby. On this tiny moon, the same toss might send the pebble into orbit or even into interplanetary space. Drop water from your hand, and droplets drift slowly, easily escaping if nudged. This demonstrates a principle that governs all small bodies. If surface gravity is too low, loose material cannot stay put, and small worlds cannot maintain atmospheres or hydrospheres. Escape velocity also explains why planetary classification depends on size and mass, not just diameter. A dwarf planet achieves hydrostatic equilibrium when gravity can overcome material strength, but it may still have an escape velocity low enough to prevent a permanent atmosphere. Earth's escape velocity allows it to retain gases like nitrogen and oxygen, while Mercury, smaller and less massive, cannot retain a thick atmosphere. Tiny Kuiper belt objects have escape velocities so low that even weak solar radiation can strip away volatile ices. Gravity is not just about pulling things down. It's about holding them in, sustaining structure, and controlling interaction with the environment. Another compelling way to picture gravity at small scales is with the analogy of a trampoline. Imagine a trampoline with a heavy weight at the center representing mass. The deeper the depression, the stronger the pull. A tiny object makes only a shallow dip. The surface curves gently, barely attracting objects. A larger mass makes a deeper dip, but doubling the weight does not double the curvature unless radius and density are optimized. Surface gravity, like the slope of the trampoline, depends on both mass and the distance from the center to the surface. Small changes can lead to dramatic differences in how objects move across that landscape. Rotational effects further complicate the picture. Gravity acts radially, toward the center of mass, but a spinning world introduces centrifugal force, which counteracts gravity at the equator. On small, rapidly rotating worlds, this effect is amplified. Haumea, for example, spins so quickly that it is elongated. Its equatorial regions experience slightly weaker effective gravity than its poles. On a tiny icy moon with a fast rotation, centrifugal forces could rival gravity, allowing surface material to drift toward the poles or even escape entirely. This interplay between rotation, gravity, and material strength is central to understanding how small worlds evolve. Composition is another critical factor. Ice is weaker than rock, meaning that smaller icy worlds can achieve near-spherical shapes at lower masses. Rockier bodies need more mass to overcome material strength and achieve the same gravitational rounding. Temperature matters too. Cold materials are brittle, they resist deformation. Warm interiors allow creep and relaxation, letting gravity smooth out irregularities over millions of years. Small worlds often exist in extreme cold, where ice behaves differently than rock, meaning surface features persist even as the body as a whole approaches spherical equilibrium. Even within a single object, gravity is not uniform. An irregular asteroid exerts slightly different pull at different points on its surface. Small craters, boulders, and ridges create local variations in gravitational acceleration. On a marginally spherical dwarf planet, these variations are smaller, but they still exist. Tiny worlds are not uniform. Their surfaces can be uneven, fractured, and porous. Gravity acts everywhere, but the outcome depends on scale, composition, and history. Understanding why doubling size doesn't double gravity is therefore not just a mathematical curiosity. It is essential for planetary science. It explains why small bodies behave differently, why some can retain atmospheres while others cannot, why rubble pile asteroids resist rounding, and why icy dwarf planets can form spheres at surprisingly small scales. It also informs how we design spacecraft missions, predict surface conditions, and interpret observations of distant Kuiper belt objects or exoplanets. In practical terms, the lesson is clear. A tiny world may be large enough to see, even nearly spherical, but gravity may remain weak. Walking, jumping, or throwing objects behaves very differently than on Earth. Escape velocity is low, so volatile materials can drift into space. Impacts can eject surface material more easily. Internal pressures are low, limiting geological activity. Gravity shapes everything, from surface slopes to internal layering, but only once the minimum functional threshold is crossed does it dominate completely. This threshold, visualized through escape velocity and the mass-radius relationship, becomes a powerful tool for classifying worlds. It explains why Earth, with strong gravity and high escape velocity, maintains a thick atmosphere and geological activity, while Ceres, with weak gravity and low escape velocity, is a quiet, icy world with a tenuous atmosphere at most. It explains why Pluto, Eris, and Makemake are spherical, yet lack the orbital dominance to be classical planets. The physics of small gravity governs all these outcomes. Even the smallest variations matter. Increase radius slightly, but keep mass constant, and surface gravity decreases. Increase density, and gravity grows disproportionately. The balance is delicate. For worlds near the minimum functional threshold, minor differences in composition, size, rotation, or temperature can mean the difference between a jagged rubble pile and a rounded dwarf planet. In this sense, small worlds are laboratories for gravity, showing us the precise conditions under which self-gravity begins to dominate, shaping matter into coherent, observable worlds. Escape velocity gives us the visual hook to make this abstract principle intuitive. On a dwarf planet, a tossed rock behaves differently than on Earth, revealing the world's gravitational strength in real time. On tiny asteroids, particles drift or escape entirely, demonstrating the limits of gravity at the smallest scales. By combining surface gravity calculations with escape velocity, astronomers can predict which objects can maintain atmospheres, retain loose material, or achieve spherical shapes. This knowledge becomes the foundation for understanding the broader hierarchy of the solar system, from rubble pile asteroids to dwarf planets to classical planets. Gravity at small scales teaches a profound lesson. Size alone is not destiny. A planet's pull is the product of mass, radius, composition, and rotation. Doubling size does not double gravity. Escape velocity is the physical expression of gravitational strength, and the minimum functional threshold, where gravity overcomes material strength and imposes order on chaos, defines the boundary between irregular minor objects and spherical self-contained worlds. Understanding these principles is the first step toward understanding the architecture of our solar system, the dynamics of small worlds, and the invisible forces shaping distant Kuiper belt objects. Gravity versus material strength. Why small worlds stay lumpy. Gravity is a silent sculptor. On large planets, it dominates absolutely, pulling rock and ice into a near-perfect sphere, smoothing mountains, filling valleys, and defining the world's very shape. But on smaller worlds, gravity is weak, and another force quietly fights back, the intrinsic strength of the material itself. Rock has tensile strength, ice has its own deformation limits. Together, these material properties determine whether a body succumbs to gravity or stubbornly resists, remaining jagged, lumpy, and irregular. Rock is strong. Even on Earth, granite can support towering mountains because its tensile and compressive strengths counteract the downward pull of gravity. Tensile strength measures the force required to pull a material apart. Compressive strength measures resistance to crushing. On a small asteroid, the same rock doesn't feel the intense pull of Earth's gravity. Its material strength dominates entirely. Individual boulders and layers of rock resist rearrangement. Even when gravity acts on the aggregate, it is too weak to overcome these forces, and the body retains sharp edges, deep cracks, and uneven surfaces. Essentially, the rock holds itself together against gravity's gentle tug. Ice behaves differently, particularly at the frigid temperatures of the outer solar system. Unlike rock, ice is weaker and more ductile over long timescales. It can flow, slowly deforming under its own weight in a process known as creep, where molecules gradually slide past each other. On a small icy world, the internal temperature, however low, determines how effectively gravity can pull the ice into shape. At extremely low temperatures, ice becomes brittle, and gravity struggles to deform it. Small icy bodies may partially relax into rounder shapes over millions of years, but many remain irregular, retaining ridges, craters, and fractured terrain. Ice is simultaneously easier to shape than rock and more easily frozen into resistance, depending on temperature and pressure. Internal pressure is the hidden arbiter of whether a small body becomes round or remains lumpy. Every particle inside a planet or dwarf planet contributes to the weight pressing down on layers beneath. On large worlds, the pressure in the interior can reach millions or billions of pascals, overwhelming even the strongest rock. Mountains flatten, craters slump, and the body achieves hydrostatic equilibrium. On small bodies, internal pressure is minimal. Gravity is weak, and the pressure at the center may never exceed the material strength. The result is that the object can remain a chaotic pile of rock or ice. Even impacts, which might otherwise help reshape the body, only leave scars rather than driving relaxation toward a spherical shape. This interplay between gravity and material strength explains a fundamental rule in planetary science. Small bodies stay lumpy. Asteroids a few kilometers across, icy Kuiper belt objects under a few hundred kilometers, and tiny moons orbiting gas giants all resist complete rounding because the internal pressure never surpasses the cohesive strength of the material. They are governed more by the rigidity of rock and ice than by the gentle tug of gravity. The boundaries of the object are irregular, the surface is jagged, and loose material may dominate over cohesive mass. Rotation can also tip the balance. On small bodies, even moderate spin introduces centrifugal force that counteracts gravity. For weak gravity and strong material, this means the body can flatten or elongate slightly, adding to its irregularity. Haumea is an extreme example, a fast-spinning icy dwarf planet, elongated due to the combination of rotation and the limits of ice deformation. Even when internal pressure is enough to shape the body, centrifugal force creates a stable, non-spherical equilibrium. Ultimately, the competition between gravity and material strength determines the architecture of the solar system. Large planets dominate, smooth and round, while smaller worlds defy uniformity. Understanding this balance allows scientists to predict the shape, stability, and evolution of bodies from asteroids to dwarf planets. It explains why the asteroid belt is full of irregular rocks, why Ceres is just barely round, and why icy Kuiper belt objects vary in form depending on composition, size, and spin. Gravity is persistent, but material strength fights back, and only when gravity overwhelms this resistance does a body become a fully spherical, self-contained world. In this delicate dance between pull and resistance, we see the hidden laws of planetary formation at work. It is a story written not just in orbits or distances, but in the molecular bonds of rock and ice, in pressures deep inside tiny worlds, and in the patient, inevitable reach of gravity shaping matter over millions and billions of years. Every lumpy asteroid, every nearly spherical dwarf planet, every fractured icy moon is a testament to this balance, a cosmic tug-of-war between the pull of gravity and the resilience of material itself. The critical radius, when worlds start to round. In the grand architecture of the solar system, there is a boundary, subtle but decisive, that separates chaos from order. It is the line where gravity finally overpowers material strength, where a body can shed its ragged edges and start behaving like a proper world rather than a haphazard pile of rubble. Scientists call this the critical radius. It is not arbitrary. It is a measure of physics, a scale set by the delicate interplay between the pull of gravity and the resistance of the material itself. And it is here that the difference between a lumpy asteroid and a round dwarf planet becomes clear. For rocky bodies, composed mostly of silicates and metals, the critical radius lies somewhere around 300 to 600 kilometers. Below this size, the rock is too strong relative to the planet's weak gravity. Mountains can remain tall, craters sharp, and edges jagged. Even over millions of years, there is simply not enough pull to overcome the tensile and compressive strength of the material. But as a rocky world crosses this threshold, the balance tips. Gravity begins to dominate, forcing the interior to compress, the surface to relax, and the body to adopt a spherical shape. It is not instant. The rounding occurs slowly, almost imperceptibly over geological time, but the process is inexorable once the critical radius is reached. Icy bodies tell a different story. Ice is weaker than rock, less able to resist deformation, and more sensitive to temperature. For icy objects, the critical radius is smaller, roughly 200 to 400 kilometers. This is why distant Kuiper belt objects, though tiny by planetary standards, can appear nearly spherical. Ice flows over long time scales, creeping under even modest gravity and allowing the body to smooth out irregularities that would remain stubbornly permanent on rocky worlds. Composition matters. The weaker the material, the smaller the mass required to reach hydrostatic equilibrium. Temperature further complicates the picture. Cold materials resist deformation. Frozen ice becomes brittle, and rock becomes rigid. But if the interior is warmer, materials can weaken, allowing gravity to shape them more efficiently. On icy bodies far from the sun, even minimal internal heating, from radioactive decay or tidal flexing, can allow ice to flow, slowly rounding the body. On rocky worlds, internal heat from formation or radioactive decay similarly reduces material strength, enabling gravity to overcome resistance at lower radii than would be possible if the body were completely cold. The critical radius is therefore a moving target, dependent not just on size, but on composition, internal structure, and temperature. A rocky asteroid at 350 kilometers might remain irregular if cold and solid, while a warmer icy body of 250 kilometers could become nearly spherical. These thresholds explain why Ceres' round yet smaller rocky asteroids like Vesta retain their jagged shapes, and why Pluto, Haumea, and Makemake achieve spheres despite their small sizes compared to the classical planets. The critical radius is the physical demarcation where gravity begins to win the tug-of-war with material strength. Below this radius, objects are governed by the bonds and rigidity of their constituent materials. Above it, gravity dominates, imposing order, shaping interiors, and creating the spherical worlds we recognize as dwarf planets and planets. It is the quantitative rule behind the qualitative differences we observe, the distinction between rubble piles and worlds, between irregular rocks and gravitationally sculpted spheres, and between chaos and structure in the solar system. Why asteroids aren't round. Walk through the asteroid belt in your imagination, and what you see is chaos frozen in stone. Unlike planets or dwarf planets, asteroids refuse to obey the simple, elegant rule of hydrostatic equilibrium. They remain jagged, lumpy, irregular, a testament to the subtle struggle between gravity, material strength, and motion. Understanding why these tiny worlds don't round themselves requires looking closely at the forces at work and at the objects themselves. First, consider gravity on asteroids. Unlike Earth, Mars, or even Ceres, the gravitational pull at the surface of a small asteroid is minuscule. These objects are too small to generate the internal pressure needed to overcome the tensile strength of rock. Instead of being dominated by a uniform inward pull, their gravity fields are irregular, sometimes stronger in one region than another. On a jagged asteroid, the force pulling a rock toward the center can vary dramatically from point to point. Mountains don't slump, valleys don't fill, and the surface keeps its chaotic character because gravity is simply too weak to enforce a round shape. Next, many asteroids are rubble piles rather than monolithic rock. They are loose collections of fragments held together gently by their own feeble gravity, often remnants of ancient collisions. In these structures, individual boulders can maintain their positions without being compressed into a uniform mass. Even when gravity acts, it can only nudge pieces into slight rearrangements. It cannot smooth out the overall shape. A rubble pile asteroid is essentially a cosmic jigsaw puzzle loosely pressed together. Tilt it, shake it, and the pieces shift, but they resist forming a perfect sphere. Spin adds another layer of complexity. Tiny bodies are susceptible to the Yorp effect, a phenomenon where sunlight, absorbed and re-emitted as heat, gradually alters an asteroid's rotation over time. Some asteroids spin faster and faster until centrifugal force nearly matches the weak pull of gravity at the equator. Beyond a certain point, the asteroid cannot hold itself together, leading to material shedding, equatorial bulges, or elongation. This is why even some rubble pile asteroids, if they spin rapidly, form elongated or peanut-like shapes, rather than rounding themselves. Rotation competes with gravity, and on these small worlds, rotation often wins. Several case studies illustrate these principles vividly. Eros, visited by the Near Shoemaker mission, is roughly 34 kilometers long and shaped like a stretched peanut. Its surface is covered in boulders, craters, and regolith, with gravity too weak to flatten the irregularities. Bennu, examined by NASA's OSIRIS-REx, is a roughly 500-meter wide rubble pile, spinning so slowly that its weak gravity barely holds loose rocks, yet fast enough in certain spots to allow dust to migrate toward the equator. Ryugu, studied by JAXA's Hayabusa 2 mission, is another spinning rubble pile asteroid, oblate with a distinctive equatorial ridge caused by centrifugal effects. Each of these worlds tells the same story. When gravity is weak, material strength dominates, rotation modifies shape, and irregular forms persist over billions of years. Asteroids aren't round because they are too small, too weakly held together, and often spinning in ways that exaggerate irregularity. Their shapes reflect a delicate balance between feeble gravity, internal cohesion, and external forces like solar radiation. While planets and dwarf planets achieve near-perfect spheres, asteroids embrace chaos, remaining rugged monuments to the limits of gravity at small scales. When a world can't hold itself together, gravity is the silent architect of worlds. It sculpts spheres from chaos, flattens mountains over eons, and holds atmospheres like invisible blankets enveloping a planet. But gravity is also patient and conditional. It works only if there is enough mass to assert dominance over the forces trying to tear a planet apart. When a world is too small, too lightweight, or too hot, its gravity fails in dramatic ways, and the consequences are written in the air, or the lack of it, that surrounds it. One of the most tangible signs that a world is struggling to hold itself together is its atmosphere. Atmospheres are delicate. They rely entirely on a balance between the pull of gravity and the restless motion of gas molecules. Every gas particle is constantly in motion, jostling, bouncing, zipping through space at velocities determined by temperature and molecular mass. The higher the temperature, the faster these molecules move. Lighter gases like hydrogen and helium move faster than heavier ones like oxygen and nitrogen. Gravity must hold on to these energetic particles. The key measure is escape velocity, the minimum speed needed for a particle to break free from a planet's pull. On Earth, escape velocity is roughly 11 kilometers per second. Compare that to the thermal velocities of common gases at room temperature. Oxygen and nitrogen molecules are moving much slower than the escape velocity, so they stay bound. Hydrogen, the lightest gas, moves faster but still mostly stays, because Earth's gravity is strong. On smaller worlds, however, escape velocity drops dramatically. Mercury, with only 38% of Earth's gravity, has an escape velocity of about 4.25 kilometers per second. The Moon is weaker still, with just 1.6 kilometers per second. For these worlds, the fastest moving gas particles, the ones in the high-energy tail of the distribution, can exceed escape velocity, slipping away forever into space. This phenomenon is captured elegantly by a principle called Jeans escape, named after the British physicist Sir James Jeans. Jeans described the statistical process by which high-energy molecules in the tail of the velocity distribution overcome gravity. Even if most gas molecules are moving slowly enough to stay bound, the few that exceed escape velocity eventually drain the atmosphere over millions or billions of years. It is a slow but relentless process, a cosmic sieve that separates worlds that can keep their air from those that cannot. Mercury is a striking example. At first glance, it seems like it should be a simple rocky planet with an atmosphere similar to Earth. But its small size and proximity to the Sun create a perfect storm. Solar heating increases the thermal velocity of gas molecules, especially hydrogen and helium, allowing them to reach speeds that exceed Mercury's weak escape velocity. Over billions of years, most of the primordial atmosphere was stripped away, leaving Mercury with only a tenuous exosphere composed of trace atoms sputtered off the surface by solar wind and micrometeoroid impacts. Mercury survives, but barely. Its gravity is too weak to retain a substantial atmosphere, and its tenuous gases are constantly replenished by external processes rather than sustained by internal gravity. The Moon tells an even starker story. With a radius just over a quarter of Earth's and mass only 1/8, its escape velocity is extremely low. Any gas particle that ever had significant motion, especially hydrogen, helium, or even water vapor from volcanic outgassing, had a near immediate path to freedom. Today, the Moon's atmosphere is essentially non-existent, only a few molecules per cubic centimeter. Any release of gas from impacts or degassing vanishes almost instantly. Gravity cannot hold it together. The Moon is a world stripped bare, a stark example of how the atmosphere test defines planetary limits. The atmosphere test reveals more than just the presence of gas. It tells us about a world's functional threshold for gravity. If escape velocity is lower than the thermal velocity of common atmospheric molecules, the planet cannot maintain an envelope of air over geological timescales. If gravity cannot overcome thermal motion, the body becomes a vacuum chamber in space, incapable of sustaining water, weather, or even a breathable layer of nitrogen and oxygen. This threshold is one of the most dramatic demonstrations of gravity's minimum functional strength. It also illustrates why composition, distance from the Sun, and temperature matter so much. A small icy world in the Kuiper belt may be similar in size to Mercury, but its frigid temperatures slow the thermal motion of gas particles, making it slightly easier to hold onto volatiles like nitrogen or methane. Closer to the Sun, even larger bodies can struggle to retain their atmospheres if their surface temperatures boost molecular speeds beyond escape velocity. This is why Venus, despite being smaller than Earth, retains a dense, crushing atmosphere. Its escape velocity is sufficient relative to the thermal motion of carbon dioxide molecules at its temperature, while Mercury cannot hold even light gases. Venus's escape operates quietly but inexorably. Unlike catastrophic events, it is subtle. A few particles leak away at a time, the tail of a distribution slipping past the edge of a gravitational net. Over millions or billions of years, this continual loss can completely strip a planet or moon of its primordial atmosphere, leaving only secondary atmospheres created by volcanic outgassing, impacts, or chemical reactions. The Moon, Mercury, and even smaller bodies like Mars illustrate the principle beautifully. Mars, with its intermediate size, retains a thin atmosphere because its gravity partially counteracts thermal motion, but it has still lost much of its early atmosphere to Venus's escape and solar wind stripping. This balance between gravitational pull and molecular motion is not just theoretical. It defines what a world can and cannot do. A body that cannot hold an atmosphere is limited in almost every way. Water cannot pool on the surface, weather cannot exist, and the planet becomes sterile in the extreme sense. Gravity's failure to dominate in this realm is a literal test of planetary viability. Surface features, internal heat, and geological processes are all affected by the absence of an atmosphere. Without the cushion of air, erosion is minimal, temperatures swing wildly, and radiation reaches the surface unmitigated. The very habitability of a world is contingent on gravity crossing this critical threshold. Even today, spacecraft provide live examples. Instruments orbiting Mercury detect only a tenuous exosphere, atoms sputtered from the surface by solar wind and meteoroid impacts. Lunar orbiters measure minuscule densities of gas that dissipate within hours. Compare this to Earth, with its thick envelope of nitrogen and oxygen, held tightly by gravity despite solar heating. The difference is entirely a question of mass, radius, and the velocity of gas molecules, a direct application of the atmosphere test. The implications extend to exoplanets as well. When astronomers detect small rocky exoplanets close to their stars, they must calculate escape velocities against expected thermal motion to estimate whether any atmosphere can survive. Many Earth-sized planets in extreme proximity to their stars likely lose atmospheres entirely within a few million years, leaving barren rocks that orbit like moons of the void. This is the same principle that stripped Mercury, failed the Moon, and continues to define the line between barren asteroids and living, breathable worlds. The atmosphere test is gravity's proving ground. A world may have mass, may even be spherical, may appear planet-like, but if it cannot retain gas against thermal motion, it is fundamentally limited. Mercury barely survives, clinging tenuously to traces of atmosphere. The Moon fails completely, an airless monument to the limits of small gravity. The test is simple, elegant, and quantitative. Compare escape velocity to molecular speed. If the molecules win, the planet cannot hold itself together in any functional sense. Surface gravity thresholds and internal differentiation failure. Walk across a small asteroid or tiny icy moon, and the experience would feel alien. The ground beneath your feet is barely tethered by gravity, and every movement can launch objects into space. Surface gravity is the force that dictates how a world behaves, controlling everything from walking and jumping to the retention of dust, loose rocks, and gas. On small bodies, gravity is so weak that simple actions, throwing a rock, stepping hard, or even vibrations from a passing lander, can overcome the pull holding material to the surface. On worlds where gravity is marginal, loose material does not sit still. It migrates, drifts, or even escapes entirely. Regolith, the layer of dust and fractured rock coating many small bodies, behaves unusually under weak gravity. On Earth, sand and soil settle firmly, bound by gravity and friction. On a tiny asteroid, however, this same material is prone to leakage. Tiny impacts or thermal fluctuations can loft dust grains into micro-orbits around the body or eject them completely into space. Electrostatic charging intensifies this process. Solar ultraviolet radiation and the solar wind can impart electrical charge to fine particles, generating forces that rival or even exceed the local gravity. This is why missions to asteroids like Itokawa, Bennu, and Ryugu observed grains moving slowly across the surface or escaping entirely, creating a kind of miniature dust storm in a gravity so weak that even a gentle push sends particles flying. Walking on such a body would be almost surreal. A person or rover weighing only a few kilograms relative to Earth's gravity could leap tens of meters with a single step. Objects tossed upward never behave as they do on a planet. They drift, orbit temporarily, or escape. Loose rocks are never fully stable, bouncing and sliding under even tiny perturbations. The surface becomes a dynamic environment, constantly reshaped by micro-impacts, vibrations, and electrostatic forces. These small worlds leak matter not as a rare event, but as a fundamental feature of weak gravity, a process that sculpts their surfaces and dictates their evolution. Gravity's weakness extends inward, affecting the internal structure of these worlds. On large planets, the pull of gravity is sufficient to compress material toward the center, creating internal pressure that drives differentiation, the separation of a dense core from a lighter mantle. Dense metals sink, silicates float, and the planet becomes chemically stratified. This process is essential for generating magnetic fields, sustaining tectonics, and producing heat via radioactive decay in layered interiors. On small bodies, however, gravity is insufficient to create the pressures needed for core mantle separation. Rocks and ices remain mixed. Metals never settle, silicates never rise. This failure to differentiate has multiple consequences. Without a dense convecting metallic core, small worlds cannot sustain a magnetic field. Magnetic shielding is essential for protecting atmospheres from solar wind erosion and for stabilizing volatile materials near the surface. Small bodies, lacking this protection, are exposed to space weathering, solar radiation, and charged particles, further stripping loose matter and reinforcing the leakiness of their surfaces. Internal pressures are also too low to drive tectonics or significant volcanic activity. On Earth, mantle convection reshapes continents, creates mountains, and generates volcanic eruptions. On small bodies, however, heat cannot build sufficient pressure to move the interior in organized patterns. The result is a chemically mixed, geologically inert body, where surface features are dominated by impacts and minor shifts rather than internal dynamics. Even the largest craters remain relatively unchanged over billions of years, their rims and ejecta scattered but not smoothed by internal processes. Composition interacts with size in crucial ways. Icy bodies, being weaker than rock, can achieve partial rounding at smaller sizes, but even they cannot differentiate internally below a certain threshold. The weakest icy Kuiper belt objects may form spheres only in appearance, while their interiors remain a jumbled mixture of ice, rock, and voids. These mixed interiors limit not just magnetic field generation, but also heat transport. Radioactive decay or tidal flexing produces energy that cannot organize itself into convection currents or volcanism. The energy dissipates inefficiently, leaving the body cold and mostly inactive. Surface gravity and internal differentiation are intimately linked. A body must be large enough for its gravity to dominate both externally, holding regolith and dust, and internally, compressing material to allow stratification. If either fails, the consequences ripple outward. Surface material becomes mobile or escapes entirely. Internally, the world remains homogeneous, inactive, and incapable of producing a global magnetic field. Tectonics cannot operate, volatiles cannot be retained, and the planet is frozen both physically and chemically in a primordial state. Even small moons orbiting gas giants illustrate these principles. Moons like Mimas, Enceladus, and Hyperion reveal the interplay between weak gravity and incomplete differentiation. Hyperion's spongy, chaotic surface is a direct result of insufficient gravity to compact the interior and smooth the outer layers. Enceladus, slightly larger, retains a partially differentiated interior that allows limited geothermal activity, demonstrating how small variations in size and composition can tip the balance between chaos and partial order. This threshold is also crucial for understanding the potential for exoplanets or captured minor bodies elsewhere. Worlds smaller than a few hundred kilometers in radius, whether rocky or icy, cannot fully differentiate. Their surfaces are unstable, their interiors homogeneous, and their ability to retain atmospheres or generate magnetic fields is essentially nil. Any water, gas, or loose dust is transient, easily lost to space. Gravity's failure at these scales defines the line between worlds that are self-contained and worlds that are porous, leaky, and inert. Real objects at the edge of planetary gravity. Ceres is a world that straddles the boundary between minor body and dwarf planet. It sits in the asteroid belt, orbiting between Mars and Jupiter, and yet it feels like it belongs to a different class entirely. With a radius of about 470 kilometers and a mass of roughly 9.4 x 1020 kilograms, it exerts a surface gravity of approximately 0.27 meters per second squared, barely 3% of Earth's. That feeble pull is enough to reshape its surface and interior, nudging it towards spherical symmetry, but not so strong that every geological process functions as it would on a larger planet. Its shape is nearly round, almost perfectly in hydrostatic equilibrium, with subtle deviations visible in topographic measurements. Mountains exist, but they are modest. Craters are softened compared to smaller asteroids. Ceres' internal structure hints at complex processes despite its small size. Gravity, weak but persistent, has allowed partial differentiation. Models suggest a layered interior with a rocky core surrounded by a mantle rich in water ice. Observations from NASA's Dawn mission reveal evidence of a possible subsurface ocean, a layer of liquid water or slushy ice beneath its crust, maintained perhaps by residual heat or radioactive decay. This interior ocean, if it exists, makes Ceres unique among small worlds. It combines weak gravity with the capacity to maintain internal differentiation and dynamic potential, even in a body barely half the size of our Moon. The surface of Ceres demonstrates the interplay of gravity, material strength, and volatile migration. Bright spots in craters, most famously Occator crater, are deposits of salts, likely left behind as briny water seeped from the interior and evaporated. Gravity is strong enough to keep these materials on the surface, yet weak enough that ejecta from impacts can travel far, subtly reshaping the landscape over geological timescales. Landslides, cratering patterns, and tectonic-like features are all scaled down compared to larger planets. Yet they reveal that gravity is active in molding the body. Its low gravity also means that loose regolith and dust behave differently. Electrostatic forces, micrometeoroid impacts, and even thermal cycling can mobilize particles, demonstrating the delicate threshold at which Ceres' gravity operates. Ceres barely qualifies as a dwarf planet because it sits so close to the minimum threshold where gravity can dominate over material strength. If it were any smaller or less massive, its rocky and icy material would resist rounding, leaving a more irregular shape. If it were colder, the ice in its mantle might not flow enough to achieve near sphericity. Its very existence challenges the definitions of planetary status, illustrating the limits of gravity in small worlds, and showing how subtle variations in size, composition, and internal heat can shift an object from minor body to near planet. Vesta, by contrast, is a world that almost reached the same status, yet its story is different. slightly smaller than Ceres, with a mean radius of roughly 262 kilometers and a mass of 2.6 x 10 to 20 kilograms. Vesta's surface gravity averages around 0.25 meters per second squared, marginally weaker than Ceres. Its shape is noticeably less spherical, influenced by both its smaller size and the immense impacts it has endured over time. Vesta's surface is marked by massive craters, the largest of which, Rhea Silvia, spans nearly the entire southern hemisphere and plunges to depths of over 20 kilometers. The impact history has preserved ridges, valleys, and mountains, leaving its shape irregular in places where gravity alone could not fully reshape the terrain. Despite its smaller size, Vesta demonstrates internal differentiation. Its rocky core, silicate mantle, and basaltic crust indicate that gravity once operated strongly enough to separate dense metals from lighter materials during its early history. Heat from radioactive decay and early formation allowed partial melting and core segregation, producing a layered interior. The differentiated structure is unique among small asteroids, revealing that even objects at the edge of gravitational thresholds can develop complex interiors. Gravity on Vesta, however, remained just below the level required for full spherical shaping. The combination of insufficient mass and impact modification prevented complete rounding. While the core and mantle formed, the crust remained fractured, and large impacts carved topography that gravity could not erase. Loose surface material, regolith, and debris from collisions remained scattered and mobile, influenced by weak gravity, minor seismic shaking, and thermal cycling. The equatorial ridge, a product of rotational spin, subtly exaggerates deviations from a sphere, demonstrating the role of centrifugal forces in shaping small worlds that lack strong gravitational control. Vesta's surface also tells a story of limited material retention. Ejecta from impacts can reach escape velocity more easily than on Ceres, and smaller fragments have been observed escaping entirely, seeding the asteroid belt with meteorites. Gravity is enough to hold the bulk of the body together, but insufficient to retain all surface material indefinitely. Dust, pebbles, and small rocks drift over time, responding to solar radiation, micrometeoroid impacts, and electrostatic forces. The landscape is alive in slow motion, a record of the delicate boundary between gravitational dominance and material freedom. Comparing Ceres and Vesta illustrates the razor's edge on which planetary gravity operates. Ceres, larger and icier, achieves near sphericity and retains internal activity like brine movement or a subsurface ocean. Vesta, slightly smaller and rockier, differentiates internally yet remains visibly irregular, sculpted by impacts and constrained by gravity that never fully dominates. Together, they provide a laboratory for understanding the minimum thresholds of planetary gravity, the physical limits at which objects can shape themselves, retain materials, and achieve near-planetary behaviors. Pluto and Haumea, gravity at the edge. Pluto occupies a strange place in our understanding of planetary gravity. At a radius of about 1,188 kilometers and a mass of 1.3 x 1022 kilograms, it is tiny compared to the classical planets, yet large enough for gravity to nearly dominate its behavior. Its density, roughly 1.86 grams per cubic centimeter, reflects a mixture of rock and ice, and this combination plays a critical role in its physical structure. Gravity at Pluto's surface is weak, about 0.62 meters per second squared, barely 6% of Earth's pull, yet it is sufficient to round the body into an almost perfect sphere. Mountains, valleys, and plains exist, but the force keeping these features in place is marginal enough that minor processes, impact ejecta, sublimation, and seasonal volatile shifts, dramatically shape the surface. Pluto's atmosphere illustrates gravity's delicate balance. Primarily nitrogen with traces of methane and carbon monoxide, it is tenuous and highly sensitive to temperature. Seasonal cycles dramatically influence its density. During Pluto's long elliptical orbit, when it is closer to the Sun, surface ices sublimate, feeding the atmosphere. Farther out, gases condense back onto the surface, causing near-total atmospheric collapse. Gravity is strong enough to hold the gas at perihelion, but weak enough that escape velocities are modest. Thermal motion allows lighter molecules, and occasionally even heavier ones, to drift into space over time, and the interplay between temperature, molecular speed, and surface gravity defines the limits of Pluto's envelope. Escape velocity is central to understanding Pluto's borderline status. At roughly 1.2 kilometers per second, it is significantly higher than the Moon or Mercury, allowing the planet to retain most of its nitrogen and methane for billions of years. Still, the tail of the molecular distribution allows some permanent leakage. This delicate balance between surface gravity and atmospheric retention makes Pluto an ideal case study for worlds where gravity almost succeeds, but never achieves the same dominance found on larger planets. It is a place where matter can be loosely held, yet never entirely free, where seasonal changes visibly reshape the world in ways that stronger gravity would suppress. Haumea, by contrast, presents a dramatic counterpoint, where gravity is tested not by mass alone, but by extreme spin. At roughly 1,500 kilometers along its longest axis and just 500 kilometers across its shortest, Haumea is elongated due to its rapid rotation, completing one spin in just under 4 hours. Gravity struggles to impose spherical symmetry against centrifugal forces that are a significant fraction of its weak surface pull. The resulting ellipsoidal shape is unlike anything seen in classical planets. A distorted figure stretched along its equator, flattened at its poles. Haumea's rapid spin reveals gravity's limits in stark relief. Surface material along the equator experiences a net force far weaker than at the poles, a combination of rotation and low mass that approaches the threshold at which regolith, dust, or small boulders can be lofted or even escape entirely. The shape of Haumea encodes the balance between gravitational cohesion and rotational stress, demonstrating that even a body with sufficient mass to round itself can be prevented from achieving true sphericity if centrifugal forces compete. Its surface, marked by icy terrain and large-scale variations, reflects this tug-of-war, and its retention of a modest atmosphere, if any, is likewise limited by weak gravity combined with rotational effects. Together, Pluto and Haumea illustrate extremes of small-body gravity. Pluto demonstrates a body large enough to achieve near sphericity and retain volatiles despite low surface gravity, while Haumea shows how rotation can offset gravity's influence, stretching a world into an ellipsoid even when the mass is sufficient to form a sphere under static conditions. Their sizes, densities, and rotational properties highlight the threshold where gravity transitions from dominant to conditional, revealing the physical rules that govern the borderline between dwarf planets, minor planets, and irregular small bodies. The smallest possible planet. Defining a planet is deceptively complex. Beyond the debates of astronomy committees and political labels, a planet is a physical object governed by gravity. Strip away the International Astronomical Union's categories, strip away Pluto controversies and name debates, and what remains is a world defined by its ability to hold itself together. Gravity is the criterion, not politics. A planet is a body whose own mass dominates over the internal strength of its materials, shaping it into a sphere, retaining volatile compounds, and generating enough internal pressure to drive differentiation, partial melting, or even tectonic processes. These are measurable physical traits: self-rounding, material retention, and internal pressure. Self-rounding is the most visible signature of gravity's victory. A body must be large enough that the pull toward the center exceeds the tensile strength of its constituent materials. Below this threshold, rocks and ice resist deformation, mountains remain sharp, craters stay jagged, and the world remains irregular. Gravity must also be strong enough to retain material on the surface. Dust, regolith, boulders, and gases must be bound tightly enough to avoid constant leakage into space. Electrostatic forces, micrometeoroid impacts, and thermal motion of gas molecules all act to remove material from small bodies, and only sufficient gravity can counter these losses. Finally, internal pressure matters. A body must be massive enough to compress its interior, enabling differentiation, the separation of dense metals from lighter silicates or ices, and generating the forces needed to drive heat transport, potential volcanic activity, and chemical segregation. Without internal pressure, the interior remains a homogeneous mixture, and tectonics, volcanism, or a magnetic field become impossible. Calculating the absolute minimum size for a gravitationally functional planet depends on composition. Rocky planets, composed of dense silicates and metals, require roughly 600 to 800 kilometers in diameter to meet the criteria for self-rounding, material retention, and internal pressure. At this scale, gravity is barely strong enough to overcome the tensile strength of rock, producing a nearly spherical shape. Surface gravity hovers around 0.2 to 0.4 meters per second squared, weak, yet sufficient to keep most loose material from drifting away. Internal pressures are modest, just enough to allow partial differentiation between core and mantle, though tectonics and volcanism would be limited compared to larger planets. Icy planets, in contrast, require slightly smaller diameters because ice deforms more easily than rock over geological timescales. For an icy body, the minimum diameter is roughly 400 to 500 kilometers, depending on temperature. At the low temperatures of the outer solar system, ice is brittle, but internal heat from radioactive decay or tidal flexing allows slow flow, enabling self-rounding. Surface gravity is weaker than that of a comparable rocky planet, typically around 0.1 to 0.3 meters per second squared, but sufficient to retain some volatiles such as nitrogen, methane, or water vapor. Internal pressures remain low, permitting partial differentiation of ice and rock, but insufficient for robust tectonic activity. Below these thresholds, bodies no longer function as true planets in a gravitational sense. A rocky world smaller than 600 kilometers in diameter resists rounding. It remains lumpy, often appearing as a highly irregular asteroid or a transitional dwarf planet. Loose material migrates easily, regolith escapes, and internal pressures never allow true core-mantle separation. Atmospheric retention is negligible, and any volatiles quickly escape into space, leaving the body inert and exposed. For icy bodies below 400 kilometers, the situation is similar but compounded by temperature effects. Surface ices may partially flow, but weak gravity combined with cold, brittle interiors prevents full rounding. Loose ice or dust may drift, and seasonal sublimation can lead to temporary exospheres that vanish as quickly as they form. The interior remains largely unmixed, and differentiation is minimal. Beyond these limits, objects transition into planetesimals, the building blocks of planets. These bodies range from tens to hundreds of kilometers and are primarily shaped by collisions, accretion, and random gravitational aggregation rather than their own gravity. They retain no significant atmosphere, cannot differentiate internally, and their surfaces are dominated by regolith, boulders, and impact craters. Material escapes easily, and centrifugal effects from spin can exaggerate irregularities. Smaller still, bodies become debris, rocks, fragments, and dust scattered throughout a star system, entirely dominated by external forces rather than their own gravity. These objects may orbit larger planets or the star itself, but they cannot hold themselves together, round themselves, or retain material over any significant timescale. Gravity is effectively negligible, leaving composition and material strength as the dominant factors shaping the fragments. The thresholds for gravitational functionality define the landscape of the solar system. They explain why Ceres, at roughly 940 kilometers in diameter, barely qualifies as a dwarf planet, while Vesta, smaller and less rounded, falls short. They also clarify the boundary between icy Kuiper belt objects that appear spherical and the countless smaller icy bodies that remain jagged, fractured, or porous. Size, mass, composition and temperature combine to determine whether an object behaves as a self-contained planet, a transitional body, or debris incapable of holding itself together. Exoplanets and extreme cases. The search for planets beyond our solar system has revealed worlds that push the very limits of planetary gravity. NASA's Kepler mission revolutionized our understanding, detecting thousands of exoplanets, including some of the smallest ever observed. These tiny planets orbit close to their host stars, often in extreme conditions, and provide a laboratory for testing gravity in situations that do not exist in our own solar system. Some have radii just slightly larger than Earth's moon, densities that suggest a mix of rock and metal, and orbital periods of only a few hours or days. Ultra-short period planets are among the most extreme cases. They orbit their stars in less than one Earth day, enduring tremendous stellar radiation and tidal forces. Their gravity must compete with the star's pull, attempting to hold their surface material and atmospheres in place. Observations of these planets reveal densities higher than Earth's, suggesting that only the densest, most massive small planets survive this environment. Lower mass bodies would be stripped bare by the intense radiation, losing any atmosphere and potentially even outer layers of rock. Gravity is tested here against the extreme energy of a parent star, and only those planets where the escape velocity exceeds the thermal motion of surface atoms can retain matter over long timescales. Density measurements are critical for understanding how small planets maintain cohesion. By combining transit and radial velocity observations, astronomers estimate mass and radius from which surface gravity can be derived. Some of the smallest exoplanets detected, like Kepler 37b, have a radius slightly larger than the Moon, with very low surface gravity, incapable of holding an atmosphere or driving geological activity. These worlds resemble solar system asteroids more than planets, yet they orbit stars directly, providing a unique view into the limits of planetary formation and gravitational control. Stellar stripping is a constant threat for small exoplanets. Intense ultraviolet radiation heats the upper layers of an atmosphere, giving gas particles enough energy to reach escape velocity. On a small, low-gravity planet, this can result in rapid atmospheric loss. Even a planet that initially forms with volatiles can be reduced to a barren rock over millions of years. Observations of exoplanetary systems show a clear threshold. Below a certain size and mass, gravity cannot prevent stellar winds from eroding both atmosphere and surface layers, leaving a dry, inert world. Some exoplanets exist in conditions so extreme that gravity struggles even at planetary size. Lava worlds, orbiting close to their stars, experience surface temperatures high enough to melt rock. Their surfaces form molten oceans, and vaporized material can escape if the planet's gravity is insufficient. For these worlds, gravity and heat interact in complex ways. High surface gravity can retain some material, but for smaller planets, vaporized rock and volatile compounds are lost continuously, reshaping the planet over time. Observations suggest that planets smaller than roughly 0.5 Earth radii struggle to retain anything beyond solid cores when subjected to intense stellar radiation. Gravity is never absent, but in these extreme cases it is insufficient to dominate. The interplay of size, mass, composition, and environmental forces defines whether a planet can hold itself together in the face of stellar energy. Ultra-short period planets and lava worlds exist as living proofs of the delicate thresholds where gravity is tested against external forces far stronger than those in our solar system.